All right, Howard, it's the top of the hour, and I'd like to welcome everyone to today's training course entitled Generator 101, taught by Professor Howard Moudy of National Electric Coil. If you thought that the Super Bowl halftime show was entertaining, you're in for a real treat today. So I'd like to take this opportunity to let everyone know that we can use the chat to send in questions and comments. There's also a raise hand button down at the bottom of your screen. You can use that if you'd like to unmute yourself and make a comment or ask Howard a question throughout the presentation. So I would say just let's get rolling. Howard, over to you.
All right, thanks so much, Scott. Good morning, everyone from Pittsburgh, Pennsylvania. It's good to be with you today. We're going to be talking about generators, and since we're really trying to accomplish an understanding overall of what a generator is and what the components are and how they all work together, we're going to start with some of the basics. And basically, the generator rotor itself, the rotating element inside this little high school experiment you see right here, it's just an electromagnet. It's an electromagnet, has wires wrapped around it, so it magnetizes the steel bar, or what would be the rotor, okay? And that's spinning because of the prime mover, the turbine, whether it's water, wind, gas, steam, doesn't matter. The prime mover turns that magnet. And back in 1823, William Sturgeon figured out that current that runs through a copper wire wound around that piece of iron makes it a magnetic field. So this becomes a big magnet, the rotor inside the generator. And if we spin that magnet, it has to take and cross the coils that you see in the stator, these copper lines you see going around the item there. Here, let me see if I can get a laser pointer so it's a little better. These are all the copper coils that are going around the stator. And we look at Faraday's law from later in the 1800s. He said that a magnet moving across a copper conductor, here's our magnet, the rotor, moving across this copper conductor, generates a voltage and a current in that conductor. So the stator then has an induced voltage and current, and we put that out on the grid, and that's how we generate electricity. It isn't a whole lot more complicated than that until you start looking at the components, and we're going to do that. But from a theory standpoint, that's how a generator works. And looking at the real thing that we would talk about today, this is a hydrogen-cooled generator, but we've got the rotor here. And, again, we're talking about Sturgeon's law, that current running through the copper wire wound around a piece of iron generates a magnetic field. Up here at the top of the rotor is what we call the rotor pole, and I'll show you this again on a slide when we show the forging itself. Each one of these slots you see, they have a neighboring slot on the other side. And right about here, we'd be halfway, and all these slots are going around this pole, and then we have the mirror image on the bottom. So it's a two-pole generator, 3,600 RPMs. And it becomes a magnet because of the energy put in those coils that magnetizes that pole head, and it spins around. Up inside the stator, and we're going to get into these components in a second, these are the end windings, but in here, when the rotor is backed in its right position, that rotating magnet is going around and inducing the voltage and the current into that stator. And that's what we're going to be talking about today. Couple interesting things to point out, and it's surprising to me quite often that most people, even though they may have been around for a while, they don't always take note of a simple fact that the stator and the rotor are different types of voltage, one, and they're different magnitudes of voltage for two. The stator armature is AC voltage, and the armature word is really a European word. If you're anywhere in Europe or many other parts of the world, they refer to as the stator itself as the armature. In the States and some of the other places in the world, they refer to it as the stator, but these are one and the same. We're not talking about a DC armature like on a traction motor. It's this AC armature. And this is traditionally high voltage. In today's world, we're operating most of the generators at 13.8 to to 27 kV. There are a few that are getting up to 28, but that's AC voltage, alternating current. And we call it a stator here in the States because it's stationary. But again, the words stator and armature are kind of used interchangeably. Over here on the rotor, this is DC voltage. And a lot of times we get that DC voltage into the unit by an exciter, and we'll touch on that later, that's figured into that, and it puts DC voltage into the rotor, either through collector rings, which we'll touch upon, or through a dedicated shaft and butterfly couplings or something like that gets that DC voltage and current into the rotor to magnetize the pole. And these are lower voltages. We're only dealing with 125 to maybe 500. There are some machines today running up closer to 750 volts DC on some of the rotors, but they're much newer and much larger units primarily. But we understand 50 and 60 hertz, we're going to have a difference in the speed that's there, but 4 poles would be 1500, 1800 respectively, 3000 to 3600 respectively for the hertz issue there. But this is what we're going to do. We're going to break these two apart, and we'll talk about the stator and the rotor and a lot of their components and the pieces and how they fit together separately. So feel free to put things into chat. I did receive some questions that Scott gave me, some people asked before. I'll try to touch on them as we go through and work with these things here today. Before we get into the different components, I think it's an important thing to understand. One of the most important aspects inside of a generator is cooling. And people say, well, why is that? Well, obviously we want to keep it from burning up, but more importantly, the lack of cooling, or let's say excessive heat, the other side of the coin, tends to deteriorate insulation exponentially almost, okay? And there was a guy they called Arrhenius, and he came up with what was called the Arrhenius equation. I think he was a late 18th, early 19th century alchemist, they used to call him. And if you know the Arrhenius equation, it's a concept that says for every 10 degrees you run a material above its thermal rating, you essentially half the life expectancy of that material. And people say that the converse is also true, that for every 10 degrees cooler you run it, you theoretically can double that life expectancy. Now, I don't know about the latter part, but I can tell you for sure, the hotter you run a machine, the more it will thermally degrade the insulation materials. And we'll be seeing some different components and materials, and we'll talk about that more later. But there's really 3 cooling mediums that we use inside machines: gas, liquid, and then there's units where we actually talk about indirect and direct cooling, and we'll get to that here in a second. But just looking at gas and liquid, gas can be air, gas can be hydrogen. There are a lot of machines that have stator coils that look kind of like this picture here in the top left. And that could be just a conventional air-cooled machine, or that could be a machine that's in a hydrogen environment. The hydrogen or the air goes all the way around the coil and gets pushed through with fans and so on. And if it has it may have a TWAC, or a water to air cooler up at the top to cool air. It may have hydrogen coolers to help cool the hydrogen, different configurations. Also, when we talk about inner gas cooled or direct cooled, which is what we talk here, this would be indirect, meaning the cooling air or the cooling hydrogen is going around it. This would be what we call direct cooled. You see the copper on each side of these square tubes. The hydrogen would be running inside of these tubes. There's only one that I know of that has square tubes like that actually has air. And if any of you have a 501 D5 D5A generator, it's also called a Westac. That's one of the very unusual ones. It has an inner or direct cooled air machine. It's very unusual. And the tubes are much bigger than the tubes you see in this picture. And you may be saying, well, why? Well, it's pretty simple. You need a lot more air than you do hydrogen. In fact, it's about 3 times the size overall. Okay, so the air is not as efficient, so you need more of it, and that's why that's done. The other direct cooled, we talk about liquids, and we have oil in here, but there are very few oil machines left. A lot of the oil machines were very early vintage liquid cooled machines. There still are some, and the oil is nothing more than pretty much transformer oil, what some people used to call mineral oil or 10C oil. And most of those have been changed out, but as I said, I know of at least a couple that are still running. Most prevalent today are water cooled machines, and oil or water, they're pretty much the same. It's kind of like what you see over here in the right hand picture. Now, there's some people that ask me, well, I saw a coil cross section and all the segments were hollow. And Howard, some of these are solid in this one. Well, this is a more recent vintage machine from a liquid cooled standpoint. The original machines by pretty much all the OEMs, all of the conductors were hollow. And the reason they did that is they weren't really sure how much cooling they would get from each strand. Later, as things evolved, what they found out is they could put solid strands around the hollow strands. And by having solid strands, they had more copper, so they decreased the I-squared losses and they push more current and keep the temperature down, and made the machine much more efficient for the size. So this is a more recent version, and when you see ones that have all hollow, they're usually an older unit. Ones that have more and more solid strands around the hollow, well, those are probably newer vintages. So this gives you an idea a little bit about the cooling on the stator. When we look at the rotor, a lot of machines, especially in the combined cycle and in the simple cycle world, that are air cooled, and the air is just running around the coils and cools it in the air gap and in this area. Now there are others that are also what's called radial cooled, and they have holes that are in the slot section, and they pull air underneath of the windings and allow it to come up into the air gap. And they can also do the same with hydrogen, and those would be indirect cooled machines. Now, these two that you see to the right are a little specialized. This is a type that we say of a radial cooled, but it's actually a diagonal cooled. And GE was one of the ones that uses this most prevalent. And instead of holes vertically up through the conductors, these are at an angle. And one side of these cooling vents is angled in one direction, and the other side is angled in another direction, and it makes for an extremely efficient cooling of the copper conductor in the rotor. But it also makes for a very complicated manufacturing scenario and maintenance scenario, and it's not something that some people are familiar with. It's really a challenge. The one in the center here is another direct cooled winding, but in this case, the conductors are actually hollow. And in the one that's depicted, this is actually a 2-wire in hand copper winding. If you can look carefully, I don't think I can really blow this up, but there's a top piece of this conductor and a bottom piece. And in the middle, there's that channel that you see running in the middle. And the cooling air goes down that channel. And in this design, close to the middle of the slot, they have chimneys that will allow that to escape up through into the air gap and then be recirculated throughout the machine. So this gives you an idea. We got, air or hydrogen, conventional cooled or indirect. Then you got an inner gas cooled that you see right here. And you see a diagonal flow that's a direct cool that you see right here. Now, I don't have a picture of this, but in case anybody is wanting to ask, I'm liable to get somebody to say, well, aren't there any liquid cooled rotors? The answer is yes, there are, but the other answer is there are very few of them, and for good reason. They're a very, very big challenge to manufacture and maintain to get a liquid spinning at 1800 RPMs. And the reason I said 18 is most of those that I'm aware of are on nuclear units, and they're usually up in the 14 to 1600 megawatt range. Okay, and like I said, I've only been exposed to a few of them in my career, and they're not that common. But if you got one of those, God bless you. They're very challenging machines, but they do exist. But you're not going to see them, on combined cycle units and stuff like that. So anyway, that deals with cooling quite a bit. I threw in a couple of slides and things today just to help you in what you're doing. And I encourage all of you to take this if you find it helpful, and to print it out and use it as your go-to and write notes in it and use it. And quite often people get hung up on words and what the meaning of things are. And I thought it would be helpful to you to have some of these. And we're going to probably touch on most of these at some point in time today. I got these out of an electropedia thing. The website is up here, so feel free to access that as well. And while I'm on it, there's a tremendous amount of resources if you go looking at it. And the International Generator Technical Forum is one of them. I'll show you that later. But certainly IEEE and many of the other authorities, it's amazing with just a little bit of looking what you can actually find, and it can be pretty helpful. It's not all over your head. So I'm flattered that Scott would call me professor. I do not have an engineering degree, but I've got a lot of scars on my back for now 42 years of doing this, and I've been very fortunate to have a lot of great people helping me and sharing information with me, and I'm glad to have the opportunity to share that stuff with you today as well. All right, we're going to go through and talk specifically about the stator for a while, and we'll start with the primary components. It basically consists of a frame, the core iron, and the coils. And here's the frame out here. Some people call it all the gray iron. Has ribs inside here, sometimes posts that are round to give it mechanical support, because the frame holds up the core and the core holds up the coil. So that's basically what's going on inside. These are all your coils in here, and we'll get into the series connections and the phase connections, the phase rings. We'll get into all that here in just a little bit. You can see the phase rings down here a little bit better. Series connections, phase leads. Inside here, this is called the bore of the stator, or the core iron area, or the slot area. And the core is made up of tiny laminations, usually, I don't know, 14 to 18 thousandths thick, sometimes bigger. But they're all stacked together, and they become that iron core that the coils go around. And when that rotor is spinning, it induces that voltage and current into these stator coils. As we'll see, then it goes out on the grid. So the generator frame itself, they can take a lot of different configurations. This is an older unit, but a couple of other things you can see here with the frame. You have bearing brackets, or some people call them end bells, that you see here that fit on the end of the unit. And sometimes they'll have the bearings integral to them. And in like this case here, they have it where the bearings and the bearing assemblies come out. It's there for you. The other thing that you see here, there's, we have these coolers on this machine at 4 different corners of the machine. And if you pull this up, it looks like a huge radiator. And in this case, those coolers, I believe, are water coolers, but you can also have hydrogen coolers, and obviously it's a little bit different. Now, I saw in the chat a gentleman asked about the presentation. I believe there's an opportunity, for you to get that through Combined Cycle Journal. But if not, and you'd like to contact me, I'd be glad to try to help you. We're all about trying to educate people and help people in the pursuit of generators and stuff. Another gentleman asked about the end bells. The bearing bracket is actually probably a better word, because that's what it is. The reason they call it the end bell is quite often they're on the ends of the machine, and quite often they have a kind of a bell shape to them. So one thing you're going to learn as we go through this and we talk about different scenarios is it's amazing. Winders are very creative people when it comes to naming things. Some of the names can get a little interesting and vulgar at times, but no harm intended. But they certainly name things in an unusual way. But I believe that's why they're called end bells. They're on the ends, kind of looks like a bell in some of the designs. That's kind of why it's done that way. And I think that's about all we can really see on this picture here. Obviously, the end bells go on this end in this area. They're bolted in. Now, just to help you out a little bit, this is a hydrogen-cooled machine. And one of the telltale signs is you see the size and the girth of these end bells, and also the frame itself. It's extremely robust. As we go through and we see other pictures and so on, what you're going to learn is that hydrogen-cooled machines have to be robust because by design, they're intended to be able to contain a hydrogen explosion inside the unit should it happen. Obviously, that's not something you want to happen, but it takes solace that the machines are intended to keep that. And while we're talking about hydrogen, I want to put in a safety note. Probably won't get into it much today, but if your operation and your involvement in the operation doesn't include a good understanding of safely degassing your generator and policies on how you degas, who can degas, what your clearances are, and that kind of stuff, it's extremely, extremely important for your safety and the safety of everyone else involved to have a policy to deal with that. And by the way, I know a little bit about generators, but I just saw a picture of a gentleman that I don't know how many of you know him, but his name is Clyde Mon, and he's probably forgotten more than I'm going to know about generators. But he's visiting today, and if I get stuck, I may call on him because he's got a tremendous background. So glad to have you with us today, Clyde. So anyway, moving on. Looking inside the stator frame, couple of things. All the stuff that's coated with Gliptol out here, the red area, those are all frame ribs and so on. And we have two different designs here that we're looking at. One of these is more of a GE design, and it's got key bars that are running down into here. And in this picture, you got a gentleman down here, he's just beginning to stack. The first layer is the laminations and this restack of the stator and rebuild. In the picture to the right, this is more of a Westinghouse design, and there's a couple of things that are telltale. One, a lot of the Westinghouse units used, especially the older ones, used what they called key building bolts instead of key bars, and these are just a large round bolt that go the whole leg. The other telltale sign that this is Westinghouse, if we look at the plate down here at the bottom, there aren't any laminations in here right now. You can see the slots on the plate, but you can also see that there's a bolt hole that goes all the way around. Those bolts are called through bolts because they go through the entire core compression plate and the fingers and through the whole core. Those have to be insulated bolts so they don't become part of the magnetic circuit inside the stator. And those through bolts are pretty much, common to any of the Westinghouse or Westinghouse derivative designs that have been running around over the years. And so got two different concepts, more of a GE concept, more of a Westinghouse concept. We got key bars over here, we got building bolts over here, and that's about what we can do there. Now, the core laminations and the coatings. There's two primary ones used today. There are others, but inside the generator stators, the C3 and the C5 core plates are still pretty much common, and it refers to the coating, the C3. The C3 is an organic coating. It has a lower temperature capability, but the advantage in manufacturing is that it doesn't beat up the die that stamps them or punches them as much, okay? And it's most commonly used when punching laminations. It's a very good coating, but it certainly doesn't have the temperature capability that the C5 ceramic coating, which is actually more of a newer, but it's been around, I know, for at least 20 or 30 years and probably longer than that. But this has a much higher temperature capability. However, this ceramic coating, when you're punching it with dies, all right, it beats the daylights out of your dies to where you have to sharpen them much more frequently, and it adds to cost and it adds to time. And so the ceramic coating is used a lot more when the laminations are laser cut. And you say, well, why don't you just punch everything and use C3? Well, in our world, I think probably everybody on this call that's participating would tell us that there are times when time is of the essence. Machine is forced out of service. We're trying to get a repair done, trying to get it done quickly. The laser is very common there. Even when you're doing a minor repair or a partial restack, it's very common to go and laser cut. The ceramic does better with the laser cutting. And in some of the processes that we use when we laser cut, we usually put another coat on after it's laser cut, but the laser cutting does much better with ceramic and withstands the heat. So that's kind of the story there. All right, the stator core itself, as I mentioned to you, the stator cores are made up of thousands of laminations in most of the machines. The gentleman over here, he looks like a Las Vegas dealer dealing blackjack, but he's dealing laminations to put them in place on these key bars. This is, I believe, the same machine we saw a couple of slides ago. The only difference is he's setting on a platform, and as you can see, he's coming to the end of the stacking, and he's putting in these laminations. If you look carefully, you can see one of the joints right here and another of joints right here. Okay, so these segments get put in one at a time. Traditionally, you would have an overlap so that the next segment that gets put on top of this, it would be a joint here and a joint here. Now, there's two ways that these can be done, and there's different schools of thought, but some of the more recent time schools of thought is instead of putting them on in individual layers, there is some degree of advantage, and we won't get into it to a great extent, but you can actually what we call continuously stack or spiral the laminations up, and it does give you some minor advantages in the design and in the losses, but that's one of the considerations that your repair house or the OEMs take a look at and consider when they're putting these all together. Now, a couple things about the way this is constructed. The consistency in which these are laid is really important for a couple reasons. One, if the consistency is really good, it really maximizes the width of that slot. So if your stacking tolerance is not real good, your actual width over the length of that core would be a little bit narrow. If your stacking tolerance is really tight, like say 1/2 thousandths, well, you've got a little bit more space. May not sound like much, but that extra space can be used for insulation, and we'll talk about volts per mil later, and decrease the volts per mil. It can be used to put in copper, decrease the I-square losses, may give you enough space you could do something more with a Robel or other different aspects. So stacking tolerance is important. Some of the better ones are about 1/2 thousandths. Some people are stacking to a much lower tolerance, but stacking to a tighter tolerance is advantageous, and it really has to do with your tooling and your process. And we won't really get into that a lot, but you can see there's rods in here, and they're not just pieces from the hardware store. Those are precision ground. This is one we restacked, but they're precision ground chrome plated rods actually that help us maintain that very tight stacking tolerance. Now, we talked about cooling and the importance of cooling. So you got areas where that cooling gas can go in a lot of machines. Not all machines have them, but most of the machines have cooling vents in areas, okay? And where you have those cooling vents, you got to create that path for that cooling gas, and that's what this vent plate is that you see over here. This is a little bit of an unusual one. It's got the notches here on the back instead of a traditional key bar or a building bolt. But in any case, you can see these ribs, and a lot of times they're tiny I-beams, or they might just be a wider piece of steel. And typically they'll get tack welded in some way to one of the sheets of laminations, and they get put in periodically in order to create those vents. Okay. Now, one of the most important things to talk about when we talk about the core, aside from the material, aside from the stacking tolerance, is cores are designed to be tight. A loose core is not a good thing. All right. And you can't just throw all the laminations in and think you're going to sandwich them all together all at once, because you'd be there for quite a long time and you may not be very successful. So in most cases, OEMs and repair houses, what they will do is in the stacking operation, they will have several points at which they will consolidate the stack or press that stack together, usually using high pressure hydraulics and some special tooling. And that way, when they get to the top, like you see here, and they do the final compression, the core was pretty much consolidated along the way, and it's not such a big deal. One of the things that's often done to finish off the core is to heat it up. Some people call it seasoning, and they basically use a loop test to use flux to heat up the core and then pressure to further consolidate it. And that's how you get a finalized core that's in pretty good shape. I kind of let the cat out of the bag a minute ago. We talked about the dovetail versus the key bar, and you know the building bolt, and the building bolt, you know, being more of a Westinghouse thing, and the key bar or the dovetail here being more of a GE thing. We talk about the laminations, and I mentioned a little while ago, most common is around 14 thousandths. There are some that are a little thicker, not too many that are much thinner, but this is kind of the way it's done inside the unit. Now, the core clamping, this is how we get that thing tight once it's manufactured. And this is a very simplistic, you know, illustration you see here just to give you an idea. But over the years, it always used to bother me. I'm a two-time ex-Westinghouse guy, and I could never understand, if we go back a couple of slides, to why this Westinghouse design has twice as many bolts, essentially. You know, it's got the through bolts here, the building bolts in the back. And this GE design only has these key bars that clamp onto the pressure plates and pull it down. And these suckers tended to stay tight more than these suckers. And this has got twice as many bolts in it. I just couldn't process that for the longest time. But what actually is happening there is on the designs that use the key bar in the back and so on, this plate, the pressure plate, is usually, y'all may know what I mean by a Belleville washer or a cup washer that's used as a lock washer. This plate is kind of cantilevered like that. It's cantilevered off the back and it's cupped. And so by forcing this together, it flattens it out and it puts real good pressure on the finger plate and on the core to keep this tight. On the other design with the through bolt that we're running down the middle, all we're doing is trying to sandwich this thing together. As soon as it starts to lose any compression, it's like a snowball going downhill. It just really accelerates its looseness pretty quick. And that's why in a lot of the older Westinghouse machines, there were a lot of efforts put into core tightening, and they came out with a bulletin called OMM 99, I believe, that dealt with using a special steel called nitronics that was like a rubber band, but it was made out of steel, so they could stretch this bolt so it had more elasticity, so it gave some forgiveness. When the building bolt would start to loosen up, that cup that's in the plate helps to keep the constant tension. By putting in that flexible steel that they put in here in the through bolts, that gave them that flexibility to help maintain that constant tension and get away from that problem. So gives you a little bit of help there. And again, components that we're looking at here: pressure plate, common to most of the designs; finger plate, it extends the pressure that's coming from the pressure plate to go up the fingers that are on the sides of the slot. So this whole core that you see in red stays nice and tight during operation and overall its life. Good question. Blake asked a question: Are stators usually constructed vertically? Well, I would tell you, if I was constructing them, that would be my preference, because I like working with Mother Nature rather than against it. However, I would tell you, in the last couple of decades, there has been at least one OEM that has started doing some of them horizontally. And what they do is they take packs of the laminations and they run them into the stator core like it's the barrel of a cannon and push them in, because the whole lamination stack is consolidated in a vacuum pressure impregnation format. And that company is Siemens, just so you know. And it does take them a lot of advanced planning and preparation, and it can be costly, but they have done some horizontally. Now, on repairs, we do an awful lot of repairs horizontally, but it's typically not a full restack, because when you get much past half of the length of the core and you have it laying on its side, all those laminations that you had nice and tightly aligned, if you don't keep them tight, it kind of starts becoming like a house of cards. So, Blake, the answer is most of the folks still do it vertically. There are some methods for doing it horizontally. You can do some repairs horizontally, but they're very situational in how you have to consider it. And I hope that answers your question a little bit, and I'd be happy to chat with you more about it at another time. But I think that that should give you some insight there. All right, talking a little more about the stator core. This just gives you a real live view of what we were seeing in the last slide. Down here at the bottom, you can see this pressure plate going underneath, and that pressure plate is pushing up against the finger plates that you see right here. And there's usually anywhere from 3, 4, 5, 6 of these fingers, depending on the machine design and so on, in one segment, let's say, okay? But they all get compressed by that pressure plate, and they're compressing the fingers on the core and also push back on the back iron, or some people call it the yoke that's below the stator coils that fit into the slot. All right. And I don't think I have this later, so I'm going to deal with it while I'm looking at it here. A lot of people get confused thinking that, well, I've got to repair a bottom coil. I'll take out a couple of tops and I'll be ready to go. Well, it's not that easy. There's a thing called the throw of the coil. The throw is the distance from the top leg to the bottom leg. And if you look at wanting to get at that bottom coil, that where my cursor is at right there, you have to remove this one, this one, this one, this one, this one, and this one, and probably a few more to get at that one bottom coil. So you have to take out a throw, and usually 1 to 3 more than just the throw to be able to get out of one bottom coil. So when we have problems and you have to try to do a repair or patch something, you want to get at one bottom coil, it's a little more than that, because the top coils always goes one direction, and it could be either way depending on the design of the machine, and the bottom coils go the other, and they form a big knuckle to give you your full end volute here on the ends. And so that's just a good picture to kind of show that. So, all right, stator winding. The stator winding fits inside the core here. This is the cell portion inside the core iron. When it leaves the slot, it's getting past the finger plates right there, and it goes out into the end volute. And the end volute is this end in here, and end volute refers to a specific shape. But if you look at a coil, this one's coming out of the slot here and goes down, and then it goes to a series connection, and then it would be going back up and into the core. And the distance between here and here would be what we talked about as being the throw. Okay. We got series connections here. You're just connecting a bottom coil with a top coil. There are some deviations here. There are ones that could be full coils where this is actually a knuckle. There's others that are made in bars, and we'll get into that shortly. And they're strand connected, and there are others that today very common to use clips on bars, but there's series connections and there's phase connections. The phase connections come off the coils and they go up to the phase rings. Okay, so they can go out into the machine. The end turn is just the area from the knuckle or from the clip caps, depending on and the phase leads all the way back to the core. That's what we call the end winding, the end turn. Some people call it the end volute, and you have it on both ends of the machine. Typically, you only have phase connections, usually on the outboard side of the generator, or what some people call the connection end or the exciter end. There are some very unusual designs, but for the most part, that's where you see them, okay? And so this is obviously the exciter end of this particular generator. Some more terminology for you again. This came out of Electropedia from IEC's site. And these are some things you might want to take note of, and it'll help us as we're going through with half coil or bar and multi-turn, and we're going to get into some of those here in a little bit. So they're there for your help. Now, we're going to spend a little time talking about the stator winding and the anatomy of the slots. But the first thing we got to get a little bit of a grasp on is talking about the difference between a multi-turn coil and a Robel bar or a bar. Some people use these interchangeably. There is a whole lot of history behind that, but a bar is traditionally a half of a multi-turn coil, and I'll show you some other pictures in a moment. But a multi-turn coil, by its name, means there's multiple turns. If you look at this cutaway that we see here, you can see the green in between each of these bundles. Well, this is one turn, and it looks like it's made up of about either 8 or 10 conductors in each bundle, 2 wide by 4 or 5 tall. And then we got 1 turn, 2 turn, 3 turn, 4 turn, 5 turn. That's a 5-turn bar. All right. And so it's a multi-turn coil. Now, there are some bars that have multi-turns. They're not all that common, but usually bars that are multi-turns are limited to 2 or 3 turns. There are some unusual ones. I've seen them in some very unusual government applications that may have 5-turn bars, and they can be really, really challenging, but very unusual. A bar is usually 1 turn, okay? And it's usually robelled in the slot. We'll get to that in a minute. Further to the slot. Now you see we have green going around each of those bundles. It's important we understand the insulation. We got some insulation on these strands. That's where kind of tan colored there. And that can be a multitude of things, but most common in high voltage coils is what they call double day glass. It's just Dacron glass that's wrapped around them. And the Dacron component in that material through heat is then fused to where it's fused together. There's usually 2 layers. That's why they call it DDG or double day glass. Now, in applications where you have a very high voltage stress in the design, and this is where the design engineers would calculate and pull this all together, they can go to a material that's got a little bit more robust from an electrical standpoint, and it's usually called enamel. Enamel can be put on, and you can put on a single layer or a double layer of glass on top of that. Enamel is a little bit thinner, but it's much higher dielectric, and it's quite helpful if you've got high voltage strand to strand. Now, one of the big failure mechanisms in multi-turn coils is strand to strand. And the current potential that's available, should they have a short between them, can be quite substantial, and they lead to major failures. And that's why, as a company, our general rule of thumb is we want to have dedicated turn tape around that bundle. It's usually mica, could be anywhere from 1 to sometimes even 3 turns of that half lap mica going around that. You say, well, why? If we got enough voltage inside the strand insulation, we'll just use the strand insulation for both the strand, addressing the strand voltage as well as the turn voltage. Well, looks nice on paper, but one of the things that you're going to realize over time is that coils in the manufacturing process, coils during the winding process, and coils during operation, they see a lot of mechanical stresses. All right, let me say that again. During the coil manufacturing, during the winding of the machine, and then during operation. And because of that, it's not just the voltage stress you see on paper. It's also got to be able to withstand and be robust enough to deal with the mechanical aspects. And that's why, we traditionally will do everything we can to put turn tape into a design to help prevent having that failure. And so I'd recommend to you, if you're writing specs or looking at specs, that's a good thing to have in your spec. Dedicated turn tape, if at all possible. And usually it is, but you got to push them. So we got strand insulation, we got turn insulation. The red that you see here in this picture, this is the ground wall insulation. Now, we mentioned a term earlier. It was called VPM, okay, and it stands for volts per mil. Pretty simple, really. It's the voltage potential to ground and the millimeters of insulation, all right? And the higher that number, the more stress electrically you're putting on that ground wall insulation. So let me give you an example, or an analogy, I should say. If I had a balloon and it was designed to be blown up to 10 pounds of pressure, and I blow that thing up to 10 pounds of pressure, tie it off, and I put it on the table, shouldn't be any problem. If I take another balloon, same design for 10 pounds of pressure, but I blow this one up to 20 pounds of pressure, and thank God it doesn't break, so I tie it off and I put it on the table, which one of those balloons would pop first? And I would hope that you would agree with me that the one most likely to pop first is the one with the greatest pressure. That would be the 20 pounds. So in the balloon, it was the air pressure against the balloon wall that allowed it to fail. In this case, if you have a great deal of voltage, very high voltage stress on the ground wall, or a high volts per mil, high VPM, that's likely to fail before one that has a lower volt per mil. Over history, many years ago, but going back into the asphalt days, a lot of the machines had very low volts per mil, ratings on them, some of them maybe even down into like 30, 40, 50. Over time, as insulation systems progressed and things changed and we're trying to get more out of the machines, volt per mil started to rise. And going back into the 60s, I would say it wasn't uncommon to see designs that are 50 and 60 volts per mil. In more modern times, in the latter part of the 19th century and beginning of the 20th century, there's been some machines, especially some coming from Asia, that have run volts per mils up to as high as 80 or 90 volts per mil, which is extremely high, to the point where a lot of domestic manufacturers say we'll have to derate that machine to rewind it. You know, we won't be able to maintain that rating reliably. So volts per mil matters. And when you're choosing, there was a question early on, when you're choosing and you're planning a rewind, one of the key things that you should put in there is today, I would say, you know, most standard is 65 volts per mil or less. And in the hydro world, the Bureau of Reclamation and the Army Corps of Engineers are two that push really hard with very tight specs on coil manufacturing. And one of the ones is they usually require less than 65. I think one of them is still 62 and a half. Used to be 60 volts per mil, but that's been increased. But you should look at what you think is right for you. Talk to the coil manufacturer, talk to the company doing the rewind about what's good for them and what they're doing. You might want to mention the turn insulation as well, but these are good things to have in your spec and be considering long before you're doing your rewind, okay? Now, many of the things that we see between the top and the bottom are similar, but if you look at the bar down here, one of the things you need to take note of is you have strand insulation and you have ground insulation. You don't have turn insulation. So you're kind of alleviating one of the failure modes, okay? But one of the similarities you're going to see are the components that we're going to talk about other than the insulation. When you get the coil in, it's important to keep the coil tight in the slot for mechanical reasons and also a couple of electrical reasons that have developed in the last 30 years or so, 20 years maybe. And one of the ways that's pretty common to do that is to use side ripple filler. And you see the black that's here and it's got a wave in it. I'll show you some pictures of this in a minute, but you know, you got that wave in it. And that's driven in there with the idea that that wave is going to be flattened out, not completely, but maybe to 85 or 90% at the max. And that gives constant tension on that coil and kind of acts like the lock washer to keep that coil tight in the slot. Now, the phenomenon I mentioned, spark erosion, is a condition that's erupted in the industry on several of the machine designs and models. One in particular, the Aeropack unit. But you know, since we're talking with the Alstom Owners Group, a lot of the Alstom machines used a rolled tape system and didn't use this, and they were trying to use the sponginess of the silicon rolled tape to take it up, and they had problems with spark erosion. It's a very fast action deterioration mechanism caused by the coil being able to move in the slot, and when it moves away from the core, it discharges very high current coming from the core and damages the insulation quick in a non-cycled application. A lot of those machines can fail in as little as 5 years of operation. So I may have some pictures I can show you of spark erosion later, but the important thing to know is if you got good side ripple to keep the coil tight in there, a good mechanism for doing that, should be able to avoid it. Good question from Bosco Khan. He's asking about the ICP, and that's called the Inner Corona Protection System. The Inner Corona Protection System is probably more common on bars than it is on multi-turn coils. And what is done is it's a semiconductive layer that's put in near the copper strand stack, and it helps to equalize voltages and it benefits the design. I really need some engineering help from my folks to get into that more. But Bosco, if you want to contact me directly, I'll get you some more help on the ICP, or what's called the Inner Corona Protection System. Since you mentioned Inner Corona Protection System, I'll tell you this. There's also an outer corona protection system that's put on the outside of the coil. And most of you, if you've seen coils in the slot, they look kind of a blackish color usually. There's a very dark green colored, some of them, but most of it's a blackish color. That's a semiconductor material. And then outside of that, there's what's called the gradient, and it's a grayish color usually. And those two components go together to try to deal with the surface voltage on the coil. Theoretically, if they're doing their job right, what they do is they help as a vehicle to get the voltage dispersed so it doesn't follow a single path, which would create tracking, by the way. But it so it disperses that surface voltage to the core, and it allows it to go to ground naturally. If it does that, no harm, no foul, and you do away with the potential for partial discharge and corona, and you do away with also the issue of the spark erosion as long as the coil is tight. So we'll try to touch on that a little bit later as we go into some other slides. So thanks for the question, Bosco. All right, looking at some drawings and talking about the difference between the multi-turn coil and the bar. Over here in the drawing, you can see this is a multi-turn coil. You see we have a knuckle on this end. We got a knuckle and connections on this end. We can see from the cross section of the coil, we got 4 turns, 1 turn, 2 turns, 3 turns, 4 turns. It appears that this has dedicated turn insulation going around between them. It would also have strand insulation. It's got the wedge and the top filler and the side filler and everything that we see here. And from the end of it, we can see it's figured in. One thing that's interesting in this design, you can see this little box that has an X through it. This is called a twist transposition. It's pretty common on hydro machines, and it helps to minimize the losses inside the coil, primarily the circulating coil current, circulating current losses. And that twist kind of looks like this. And what that is depicting on the drawing is what you see right here. Okay, and it is a type of a coil transposition to help equalize the slot voltages and make the thing, a lot more efficient. All right, and it's kind of a trick in itself because you have to do this without shorting any of the strands or compromising the turn insulations on the surface. So it's an interesting manufacturing challenge. Over here, these are bars. All right, and I told you a bar, traditionally you can think of it as a half of a multi-turn coil. And so if you look at this leg, goes up here and has a connection on this end, and then you got a mirror image over here. So the two of them together make a full coil. But in this case, this is a single turn coil, and it has a Robel in each of the slots. Now the Robel name came from a guy that I believe his last name was Robel. And basically what he did is by twisting and shuffling the strands stack. If we went to this green conductor you see here on this end where my cursor's at, it transposes over to the other side and then it follows itself down. By the middle of a coil, and what they call a 360-degree Robel, 360 degrees meaning it's making a full circle, okay? It would be at the bottom and it would cross over again to this side of the coil. And then on this side, as it progressed down, it would work its way up and it ends up in the exact position it was before. So it made a complete circle around the coil. And that transposition is called a Robel. All right, and then there are a variety of different Robels, and they have to do with the degree of how it's circulating around that coil. 360 is very common. Another common one is 540. Another common one is 720, meaning so it went around the coil twice in one length of that bar, okay? And then there's also a 900, which is becoming more prevalent today. And I'm pretty proud of what we have at National Electric Coil because, we're one of the world's largest high voltage coil makers, and we've been making 900-degree Robels for a lot of the coils that we've used to rewind and help people uprate and upgrade their machines for better part of 25 years or so. But one of the OEMs has started to use it primarily on some of the global VPI machines to help minimize losses, to help allow them to put in a conventional coil into a global VPI machine. They have to offset the thermal transfer characteristics of the global VPI, And so by minimizing losses using a 900-degree Robel, that helps with that. But that tells you a little bit about the Robel. You can look in here, and usually on the drawings, if you look at it, you can tell there's a Robel. We got strand stacks, and if you look carefully, you can see a single stack at the top and a single strand at the bottom on each of the top and bottom coils. That's showing us it's a Robel coils. Sometimes it's not uncommon to see two that are Robelled at a time, and there can be more, but usually one is very common, two is not uncommon, but those are the most common configurations. And typically inside of a bar, you have two strand stacks, one on each side, with a vertical separator material in between it. Helps get it all sandwiched together. There are designs where you can have additional strand stacks and different configurations to that as we put it in there. But anyway, that tells you a little bit about the way this is. Now I have losses, manufacturing cost, winding time, and maintenance. Just to help you understand some of the commercial implications. Making this coil versus making this bar, okay, if these were put in essentially an identical machine, this bar is much more expensive to manufacture. However, depending on the configuration of the machine and the output rating and so on, voltage, this bar minimizes losses much more and is much more efficient. So it provides you with a technical performance advantage in some cases. There are cases where there have been multi-turn coils that have been upgraded and replaced with bars. This is a more expensive design to manufacture, and depending on the engineering design and so on, it may be justified and it can be looked at. So again, to the gentleman that was asking the question before the session about things to consider, this should be considered. What type of coil do you have? And is that the best coil for my machine and where I want to go? Can I consider an upgrade or an uprate? And these are things you should be talking to your service provider about, and they should be able to help you. So I hope this helps a little bit with understanding the bar to the coil aspects of the stator. All right, we talked about lowering the losses a little bit, and there are three primary losses that you see in the coils themselves. There's the I²R losses, the strand or the eddy current losses, and then the circulating current losses I talked about a minute ago. And if we looked at a conventional bar, and this is a Robel bar, the strand is not in the middle, but you can see there's heavy insulation under it, noting that it would be transposing over on the bottom and the top. And if we can find a way to put more copper inside of here, we're going to be able to decrease the I²R losses, because the quantity of copper, it's inversely proportional to the losses. So the more copper you add, the lower it is. The more copper you have, you can decrease the temperature at the existing megawatt rating, but if you put in increased copper, you can get a higher rating, but it usually would take you to a little bit higher temperature as well, if that makes sense to you. Strand or eddy current losses. This has to do with the geometry of each individual strand. And to give you an analogy, many of you may be familiar with cables. The cables itself, most of the current is carried on the cable, on the outside of the cable, and you're probably aware of that. The same way with the strand. So they made cables more effective by putting in multiple layers and different stranding and some twists. But inside of a coil, we can optimize the height and the width of that copper to decrease the strand or eddy currents. And it's proportional to that strand thickness and how you apply it. And that's one of the design characteristics you would go through. Circulating current losses has to do with that transposition we talked about, whether it's the twist or whether it's the Robel. And you can, and you do reach a point of practicality where you say, well, geez, I can add another Robel, or I can try to add a twist, but it's going to cost me this amount of money, and I don't only reduce the losses by this much. So there really isn't any value going from a 720 to a 900 or a 360 to a 540 or whatever. Okay, that can be looked at. But it may be that there is an advantage to doing that. And quite often in what we see, we do end up increasing the Robel if we have the space and have the area, because it does help a lot in the way you minimize those losses. Now, Again, we look at the thickness of that insulation, and one of the things I hate about virtual is it's hard to ask you questions, but if I had to ask you what's important about the thickness of that insulation, well, I would hope you would tell me it's the volts per mil, which is the voltage, the ground potential voltage versus the thickness of that. And as a general rule today, 65 is a nice number, but there are a lot of designs running in the 70 to 72 range. But the more you can keep that volts per mil lower, the less voltage stress you have on that ground wall. So I just wanted to reinforce that point again. Adrian asked the question, why 6-phase connections on a stator when you only got 3 phases? Well, there's a lot of different configurations, but the reason you have 2 at each position, okay, is you have a main and neutral. Now, if you're talking about why do you have 6 positions when you only have 3 phases, meaning you have it's a 2Y connected basically. Okay, so you have 2 groups of 3 phases that make that up, I believe is the right answer for that, Adrian. But again, if you want to contact me later and you have another specific question, maybe I can get into what you're seeing and help you a little better with that one. All right, slot cross section. We talked a little bit about that. Remember, we were talking about this coil. We can look at it, and I hope you would tell me it's a bar. I would hope that you would also tell me, well, it's a Robel bar, and we know that because we got 2 strands on the top, 2 strands on the bottom. That would be the Robel transposition, and they're transposing 2 in hand, or 2 strands at a time in both the top and the bottom coil. You notice how big these vents are in this particular drawing? I'm pretty sure that's the one I was telling you about that was known as the Westpac. That's the air inner gas cooled. Those are huge tubes to be inner gas or direct gas cooled. And I think that's because it's the air design, and I'm pretty sure that's where that drawing came from. But also looking at the different things, we've got the laminations out here, top coil, bottom coil, got the cooling tubes that we see inside here for the air or the hydrogen. We got copper strands in each of the strand stacks and in the transpositions. We got ground insulation. This is the area that's going around each of the coils here. And we got a top filler that's directly above the coil and so on. Quite often we'll have a top ripple spring as well. Difference between top ripple spring and the side ripple springs. Top are typically not conductive, and usually a tan or a golden color. The ones on the side are conductive, but they're cut at a 45-degree angle too. And the ones on the top are gold color, and they're usually cut at a 90-degree angle. And those are usually telltale signs for you. Also the wedge up here, and obviously the purpose of the wedge is to keep that coil tight in the slot vertically. Purpose of the side packing and the side ripple filler is to keep the coil tight side to side. Now, there was a question, and I'm going to try to address it later, early on, about how do you keep the side filler from migrating? And there are a couple of different techniques. Winders would often immediately refer to what's called a figure-8 tie. And as that side packing is put in, one of the winding processes they'll put in, and it can be put on later, is they would put a tie that goes around and snakes around this way and then comes up and puts around. And at the top up here, they tie basically a square knot. Okay, and by doing that, that tie cord they put around acts as a barrier, so both the side packing and, more importantly, the square knot keeps the wedge and any of the top filler from migrating out too. And that's one of the most common ways to keep the top and side filler and wedge from migrating. Now there are others, but that's one good one. So with that kind of takes care of that slide. I talked to you a little bit ago about the spark erosion I was mentioning to you. If you don't keep the coil tight in the slot, there is a potential for this phenomenon called spark erosion. And in this illustration you see up here, you have one part of the coil that's still in very good contact with the core, but some distance away, and the greater the distance, the bigger the interaction happens. But when it pulls away from the core, it discharges that I current from the core. And that's different from partial discharge, because partial discharge has to do with the voltage on the surface of the coil, and spark erosion deals with the high current that comes from the core. Some people call this more of an inductive event, where they call partial discharge more of a capacitive event. Okay, but we can talk about that more. But this is the end result. And one of the reasons why I put this in is we're here with the folks from the Alstom Owners Group, and there are a lot of ABB and Alstom, both legacy Alstom machines today, now all part of the GE family, but there is a lot of them that have what's called a rolled tape system. And what it does is it spiral wraps a silicon tape, and they jam that down into the slot, and they try to sandwich that silicone. And the silicon semiconductive, just like the side ripple or the side filler. And they're depending on the resiliency of the silicone to act to keep the coil tight. So its resiliency will hopefully do that. But what's kind of interesting to note too is a lot of the insulation systems we're talking about today in high voltage are epoxy, or what we call polymer systems. And any of you that have ever used 5-minute epoxy, if you take and mix up 5-minute epoxy and you drill a hole and you put that epoxy in that hole, and you take a putty knife and go across the top nice and flat, when you come back after it's cured, what you're going to find is if you look at it, you've got a dish in the top of that hole where you put the 5-minute epoxy. It didn't just settle down in there, it actually shrunk. And most epoxies, even when they're fully cured over the first in stator coil applications, it's very common for them to shrink maybe as much as 1 to 3% over the first couple of years of operation, and then they'll stabilize. But because of that, when you wind these machines, if you don't have some resiliency to keep that coil tight in the slot, it's going to move. And if that coil moves, this is the phenomenon that you may get. Now you may ask, well, what are those black lines that we see every so often? Well, if you look at it, and the nice thing about this picture, it's right up against the core. You see those vents? They line up perfectly with those black slots. You can't have the current exchange that comes from the core anywhere you got a vent slot. So all the activity is here. And there is a process for inspection where you can go through these vents and look at the side of the coil. And what you're not seeing the major activity, but you're seeing the activity that washes over. Like you see in this slot right here, maybe a little bit up here, maybe you see some here, where that, and definitely see some over here where it's washing into that slot. And when you see that, you can gauge how bad this spark erosion is getting and how close you're in danger of a failure due to spark erosion. And again, if you have a base load unit, a lot of these have failed in less than 5 years, 5 to 6 years, okay? So that's what I wanted to tell you about that. Going back to the slot, we talked about side ripple filler. This is a picture of the raw material itself. The side ripple, as I said, it's cut at a 45-degree angle, and it's basically driven into the slot, and it flattens out these ripples that you see in there, but not completely. It's very important you understand. It's not intended to go completely flat, or you can damage the fibers in the ripple, and then it won't do its job well. So when the engineers design it, they look at it and they say, okay, we're going to use a ripple filler thickness of this, and we're going to drive it in, and we're going to end up with this, and that allows it to still, leave the last, 10 or 15% left, but still give us good compression. And here you see it applied. Now, one thing, just as a curious note, is you got to be careful of what's called bird's beaking. And I told you about winders and their creativity. Again, the winders will work on this one. When you cut this material, you got to be careful of the areas that may go near the coil, because that's a pretty sharp corner right there. And over time, because the 60 cycle vibration inside the machine and other aspects, it can actually wear a hole in there. And traditionally, what you do is you try to orient it where the bird's beaking isn't against the core, or you'll take and you'll actually radius this area out so it can't be point loaded to deteriorate the insulation. But other than that, you definitely want to talk about rewinding. For the gentleman who's asking about rewind guidance, you want to require that you use side ripple filler to give you the best quality job when it's wound. And I highly recommend it. So that's a good explanation to you about ripple filler. And we talked about top filler, and we talked about the wedges. Now, unlike the ripple that's cut at a 45, and you can see it's black in color because this is semiconductive, okay? The top ripple is cut at a 90-degree angle, okay? And it's kind of a gold or a tan color, depending on the manufacturer and so on. and has the same purpose, but it's cut a little bit differently. And one of the reasons I believe that that's done is in the side, cut at a 45-degree angle, it spreads out the compression onto the coil, so the ridges are less point loaded, and it gives you more surface bearing area with the ripple than if you're using, than if you're using this 90-degree. But this is quite good in the top of the coil, works very well. And it can be used sometimes in tandem with a filler below it, but traditionally it's put in. Now, from a maintenance standpoint, I'm not positive, but I believe Westinghouse is one of the ones that introduced it, but you see these holes that are in the wedge here, and you look at the ripples in that filler. You have to imagine this is a way to check the wedge tightness by gauging the deflection, or how flat you have this, or how much it's sprung loose, okay, of this top ripple. And so you're using very tiny diameter pin mic to get down here and mic each one of these holes. And if you chart that, it will, and you connect the dots, okay, you're going to see how much this ripple is defected. And if it's, 80, 85% flat, and that's what you originally put in, well, it hasn't lost much of its compression, and you're in good shape. If it's baked back to basically what it was, it's relaxed a lot, and you may need to re-wedge and address your filler. So a lot of people call this, it's an empirical way to measure that filler. Now, here's some other wedge designs you see up here. This is an end locking wedge. That's why the herringbone design, you'd be pushing it in this direction, and then the herringbone keeps it from wanting to come out. This is just looks like low shrink black canvas in this particular picture. A lot of these over here are epoxy glass laminate, whether it's G10 or G11. G10 is pretty common. G11 is a little bit higher temperature. But anyway, you can see there's different configurations where they build in what's called tapered sliders. And what these do, when you put in the wedge, you don't have to try to drive it over to get the compression. You have a lot more room in the way you wedge, because you can use the taper and the way you drive these to adjust how much compression you're putting on the filler materials. And you might want to ask, well, what are these little notches we see over here at the side? Well, those notches are to allow the air vents to have complete circulation and so on. You see that on a lot of these. And usually they're tapered a bit, because a lot of those vent passages are oriented towards the direction of the rotation, so that it draws the air up through, and you don't want to obstruct it. So there's a couple of different things you see there. And obviously these areas that you see in between those vent areas, well, those are the areas that engage the core and allow the compression of this wedge to keep everything nice and tight. All right, we're going to move the end windings a little bit. And inside here, we've got the core of the generator, and we got the finger plate here, and then we got the end windings. We've got series connections, got a phase connection. And at each phase connection here, we've got a main and a neutral. There are some unusual machines. If any of you have, my favorite is a 324, because it's got six phase connections at each point around the machine. So it actually has 3 mains and 3 neutrals in that circuit at each phase connection. It's really an unusual machine. But the important thing I want to show you in this picture is it's important to keep this end winding consolidated. And so it has a nice hoop strength. So it's not going to move around, it's not going to vibrate, and it's not going to resonate. And we'll hopefully get into this a little bit later when we talk about resonance and we talk about vibration, but they are different. They can be happening at the same time, but vibration is a function of driving forces and so on, and resonance is a function of frequency. And if you've ever messed with a tuning fork, you'll understand what we mean by resonance. If you make that tuning fork heavier, if you touch it, if you make it more rigid, it doesn't work anymore. And resonance has to do with the natural frequency of the end winding, and we'll get into it a little bit later. And it is an important thing to prevent deterioration mechanically of the end winding. Now, the way you keep this stuff tight and make that hoop strength is by putting in spacer blocks. Some people call them diamond spacers because of their old shape, and some call it lacing and looping. Some people call it blocking. But essentially, in this case, what they're doing is putting in glass blocks with a thin felt layer on top of it that would be wetted. that acts as a conforming layer, and they would pound it down in, fairly tight without doing any mechanical damage, obviously. And then they'll lace them in place with these. And sometimes they're done with B-stage materials and cured. Sometimes they're wet wound using an epoxy and then cured with heat or just air dry. But in the end, it comes up looking like this. And one of the things that I always loved is, my grandmother was kind of funny. She used to tell me about cleanliness. Harold, cleanliness is next to godliness. And she was also a crocheter, and she used to say, symmetry is a beautiful thing. Well, as my grandmother would say, when you look at an end winding, the coil positions, the diamond spacers on all the ties, symmetry is a beautiful thing. So it should look very consistent going around, very repeatable. The spaces between the coils should be, very consistent pretty much all the way around the machines. Anyway, coil bracing systems. We've got these coils hanging out there. In the older designs, the distance from the series connections and the phase leads back to the core was not all that great, okay? Now, over time, and as designs were enhanced and upgraded and improved, and the power out of the machines became greater, what we found is these end windings were extended, okay? And they became almost like a bowl of spaghetti because the coils became a little bit narrower, a little bit taller because of the design parameters, and you had to find a way to restrain them. But even on the older ones, you had to help hold them in place because if you have operational events or if you have grid events or even bad lightning storms or weather circumstances, you need to hold these in place because the surges you can see in there from the electromechanical forces are pretty substantial. And traditionally, you would have what's called a support bracket. Some people call them gun stocks because they look like the end of a gun stock that you put against your shoulder. But that usually supports either surge rings or a cone or bigger surge rings that are on lands. But in this particular case, that bracket is tied back tight to the core by these bolts, and it's tied tight to this involute here. Now it works on a lot of these older machines and they're still pretty valuable, but on most of the newer vintage larger machines, you've incorporated a decoupling of these areas. And when we talk about the way machines act thermally, this coil, when it grows, it tends to grow axially. So the length of the coil is going to want to extend out of the slot, okay? And when it does that, if you try to restrict it a lot in here, things are going to want to buckle and do things that we don't like. So there was a period of time with designs where they made some where they had that and they said, holy cow, we're having a lot of problems with those forces that are in there. So they found ways to allow the end winding to either move on lands with the surge rings or for the coils to move on those areas so that you could allow for that axial movement of the coil when the machine heated up and when it cooled down, through your operational cycle and so on. And that's an important thing to recognize. But this is a pretty simple design. And this is not the exact machine, but this is similar. And you see you got a surge ring here, and you got a surge ring here. And they're laced into the coils. And you've got the coil support bracket over here. And it's tied tight to the surge rings. Okay. And then it's also bolted back to the core. All right. And it's not a bad system for this particular design. Now, if we go to this is a little bit different, much different machine, okay? We can tell by the piping hardware here, or the plumbing, some people call it. This is a water-cooled machine, okay? So it's a much larger machine, higher output and so on and so forth. But in any of these machines, you have a lot of radial forces that act on the coils. And so this is why we have to keep them tight. And in fault conditions, you have tremendous radial forces, as you see by all these red areas, okay? Now this is the core. Back here, this is the flux strap of the step iron here too. But back here we got this bolt here. It's not on the back of the core. So I'd love to be asking you this question and see how many of you remember. But this is probably a Westinghouse design, and that looks to me to be one of the through bolts. And you would have a building bolt back here in the back, on the back of the core too. But what's interesting about this, here's our coil support bracket, and they're supporting the phase rings here. But here's our coil support bracket, and here's a cone, okay? If you notice, that cone and the coils, they'll be tied tight together. It'll allow this thing to move a little bit on these lands, to see at each one of these places. So it gives you some axial movement. But there's another mechanism in here to also allow for movement, and that's with the coil bracket itself. You see this black line? This is actually a spring plate that's put in here, and it's affixed here to the step iron and the flux trap here, and it's affixed here to the end of the bracket, so that all of these brackets are the same design, and so it would allow this bracket, along with the whole coil assembly, to be able to move axially, and that's what you would call a decoupled bracing type of system. Okay. Now, Franco asked a question about resonant. Can it be the consequence of vibration? Vibration could mean pulsing operation. Well, the relationship, in a layman's, term, the relationship of vibration and resonance is that resonance can exhibit itself in exceptionally high vibration, but vibration does not create resonance. Resonance is created by the natural frequency of the device. Okay? And I have some pictures later, I think, talking about bump testing or a fast Fourier analysis, but in essence, if the winding, an individual coil, or some of the assemblies have a natural frequency that's approximately twice the frequency of the generator, because we have a two-pole magnet, okay, that thing is going to be in resonance. So on 60 cycle machines, if something is twice 60 hertz, so if it's within about 115 to about 135 hertz, that's what we call the exclusion zone. It's going to have some degree of resonance, and the closer it is to 120 hertz, the greater the resonance, and the greater the resonance, the greater the vibration that's exhibited. So I hope that helps you with that, Franco. But I would also say there's things you do about that. And today on rewinds, so the gentleman asked about rewinds, a bump test, especially on newer vintage machines, is an extremely important part of your spec to make sure you're not putting it back in and installing it in a resonant condition. And so what do you do if you find that the natural frequency is in line with the exclusion zone? Well, a couple things, and I may have some slides later, I can't remember, but one thing is you can add mass. By adding mass, it'll change that natural frequency. You can make it stiffer or more loose in some cases, not as many. Usually it's mass. But by making it more stiff, you also can change its natural frequency. And, there's some other minor factors, but those are the two most common corrections for resonance. So resonance is a function of its natural frequency, just like a tuning fork. And the vibration can be caused from a number of different things. It can be vibration in the frame, the foundation, the rotor itself transmitting, into the machine. There's all kinds of reasons you could have vibration, which you could see with dusting or greasing. But resonance is an exceptional condition, and it's the propensity of that assembly to vibrate more at one given frequency than any other, and that given frequency is its natural frequency. Okay, so Franco, I hope that helps you a little bit. Okay. All right, end winding stability. We talked about this a little bit. In addition to the diamond spacers and the blocks that you see right here, a lot of times on the newer design, they have clips and so on. You'll put in some series or phase connection blocking to help with that. This one out here would probably be like in a phase coil. These are more the series connections, and these would go out to the phase rings. But it's important to help add this for the hoop strength of the machine to keep it much more strong in its hoop strength ability. You can see those tapered blocks. You can see them up here in the picture in between. The reason they have this hole in the center, you can see the lacing that's going around. So not only are they put in tight, but they're laced tight. Now there are a lot of designs where this tapered block is actually in two or three pieces. Usually it's one or three. And in three pieces, you pull them together with the taper, and then you lace them all together, and it works out quite well. And obviously, this is a hydrogen-cooled winding. You see the hydrogen-cooled tubes in here. We can see this phase lead has a big hydrogen passage to allow the hydrogen to go through its path and to do its job. So I hope that helps you out just a little bit. All right, coil phase and series connections. This is just a good picture after a rewind. We'll look at some of the anatomy a little bit better. We've got the core that's in here, and this is the slot sections of the coil. The area from the end of the core out here, the series connections. This is our envolute. We got blocking and diamond spacers that you see around here. It looks pretty symmetrical, so that's good. There's an inner surge support that you see right there that's also laced in. So that's kind of quite good. That's really a nice thing. Then we got all these series connections that are all clipped and capped. And then you got blocks in between those, just like we saw there. So that's pretty cool in the way that's established. Now, and then we got the phase connections that come up here to the phase rings that go along. You have the phase connections at the different places, okay? Now on the back of the end winding, we also have some surge rings. And it's hard to see it here, but it looks like they're on lands on those brackets. So that would allow this end winding to move in and out from the expansion and contraction of the machine. So that kind of shows you everything that we've been talking about all in one nice, neat package. Obviously, this is before painting. And so that's kind of important. One of the interesting things that, to take note of is, obvious when you're painting there, if you want movement in an area, you don't want to accumulate a ton of paint. So sometimes they'll put in painter's tape to keep those areas clean so the surfaces that get painted don't restrict that movement later, or you just defeated the purpose, So that's kind of an important thing. Again, we're here at the Alstom Owners Group, and I wanted to talk a little bit about some of the bigger Alstoms, the WX, WYs, all pretty much have this configuration. And one of the things they do for their hoop strength and to make that end winding support brackets, cinched up quite tight, is they put in these tensioning blocks. I used to call them scissor jacks, but because they have this rod that pulls these two blocks that are on a taper, pulls them together, which exerts pressure between this block out here and the support that's on the back of the winding. Now that rod that goes all the way through there, it's threaded here at the end with that nut. And this is actually a stack of Belleville washers. This is a great design because it allows you the ability to tension. It really allows you to acutely get the right amount of pressure on it to make it work. However, one of the things that we found on a lot of these, and we rewind a lot of them, we do a lot of maintenance on them as well, these Bellevilles tend to yield over time and a lot of them break. We've upgraded them and made them a little bit thicker. We've made them out of a little bit different material so they don't tend to break, and so you can maintain compression. Once you lose compression of that Belleville stack, as you can imagine, you lose the compression on these blocks. If you lose the compression on these blocks, you're no longer effectively supporting the end winding, okay? And the other thing I will tell you on a lot of these Alstom machines is they do have issues with resonance. I know 2008 for me, New Year's Day, a day that will live in infamy because I was celebrating a little bit more than I probably should have the night before, and I get a call very early in the morning on New Year's Day and says, "Howard, we just blew up our machine." And I said, "Well, sucks to be you. What is it? Where is it? What'd you do?" And it ended up being one of the larger 300 MVA 21,000 volt, WX, WY machines from Alstom. And what happened is the failure occurred up in this region right here. And these phase leads that they have, when we looked at it, it just vaporized this one and it ate the corner out of this one. And this is after a rewind that we did, so you can't see the exact configuration in this picture. But when we looked at it, when we talked to the customer, we were doing it right in front of the OEM, and we expressed to them, "Hey, we really think there's a resonant condition," and the OEM told us we were full of cow hooey. And we told the customer, "Look, the first thing that we're going to do before we do anything else, if you want to work with us, is we're going to go in and we're going to bump test all these other phase rings to see what's going on." Okay. Make a long story short, they gave us the job. We went in there, and when we did that, the other 5 phase areas, they ranged anywhere from about 121 to about 126 or 127 hertz. And that means that these things had a resonant condition and they were vibrating like a paint shaker. And that's what caused stress cracks in these phase connections, which led to that failure. Now we corrected it by the geometry of those connections, putting in extra blocking that you see here. And we also put in an additional inner surge ring, I believe. We reused their tensioning devices. Now, you see all that blue that's in there? I wish I could be asking you this question, but I gave the answer before. This is before this unit's painted. We go back to this diagram. If I paint up this whole threaded rod and everything, and I paint up these areas of these lands and stuff like that, that paint will essentially glue everything in place. So this is right before painting, and they have the threaded rods covered up, and they have the areas on the slider also covered up so that it can maintain its functionality after it's painted. And then obviously it's extremely important to account for all these pieces of tape, okay, and make sure they're cleared after the painting and that these surfaces are cleared. So that gives you a little bit of help here.
Can I ask one
I
question?
see, I'm sorry?
Can I ask a question? My name is Solomon Prince. I'm from United Arab Emirates. Just now you spoke about this phase break connection failure. We have WY machines, Alstom, and then we had 2 failures so far, on these phase breaks. Actually, there was a CIB released by Alstom in 2015 after a failure in Lancashire, UK. And then subsequently, there were TILs from Ansaldo and GE, to modify this phase break connection. The reasons that they were saying is, it is due to improper bracing, workmanship issue, and also the amount of bracing in this joint is not adequate. But this bump test is something, I'm listening for the first time that this needs to be tuned as well to resolve this issue. So currently we are, this phase break failure is so severe if it happens at the bottom side, it also hurts the rotor badly. That's what happened to us actually.
I may have pictures later, and I really appreciate you sharing that with everybody. That's good information. I'll share with you a little bit more, and I probably shouldn't, but part of my discussion with the OEM, and when I told the customer we had to bump test those, they told me, well, we calculate that at the factory. And I said, well, that's good. We calculate at our factory too, but we verify. And I said, we're going to bump test the damn thing. And this plant is in the plant that I was working on at the time was up in New York City, and it was really near a wastewater treatment plant. And they said it was probably brought on by ammonia that came from that wastewater treatment plant. Actually, you got to be kidding me. This machine's been, and it caused stress corrosion cracking is what they said. And I said, there's no way. I said, first of all, the machine lasted 18 months, 2 weeks. You know what the warranty was on the unit? 18 months. That's what you call design obsolescence, okay? And I don't think it was designed that way, honestly. That's not true. But the fact that it was out of warranty and the fact that you don't get stress corrosion propagating that way, let alone I was there for 3 days and I told them I haven't smelled ammonia at all. And I said, there's a way we can find out. We can bump test, and at worst, we're going to waste a day. But I want to know, and there's good reason. There are a lot of things. We could spend a lot of time talking about it, but the design of those, I think Alstom and ABB referred to them as lugs, okay? And there were a number of bulletins put out on some of the smaller ABBs and also on the larger Alstom ones, and they had some pretty sharp geometries in the connectors themselves, the way they were blocked and the way they were held together. And there is some truth to the brazing. I believe Alstom and many of the OEMs to be quite competent, and they qualified, I believe they qualified their brazers and folks just like we do, and we put them through the reins and usually requalifying before the jobs. But that doesn't mean that you can't have a cold braze. But those are things that there are testing methods you can use to help pick those up. And by qualifying your people, there's a lot less chance of having braze problems. But you also need to be careful of what the procedure is overall. Is it a good procedure? With good trained people, will it yield consistent results consistently? Okay. And those are some things I would have to say about that. But I really appreciate you sharing that with the group. That's a very good point and very, very apropos. Hey, I should have gone one more slide because here's your problem, and this is the exact machine I was talking about. This is what it looked like when I got out the site. And this is the one phase lead. Here's the other one. But this phase lead is supposed to go all the way across to here. That's been vaporized. This is it down here cleaned up, and you can see it quite well. And the plasma ball that was created right in here had enough heat that it actually ate away at the corner of this one. But what's interesting is some of the sharp geometries they had on these connectors, okay? And the geometries, you know, alone may or may not have led to cracking. You can see the sharp geometry on this one right here. We would have rather have seen that in a nice sweep, which is the way we did it when we replaced these, by the way. But because of the resonance and the high vibration, because of the resonance, we found stress cracks in many of the other connectors. They just hadn't failed yet, okay? And we proved it by the bump test first of the other connectors that weren't damaged, and then by stripping them and cleaning them and looking for it, and this is what you found, okay? So this is a true resonant failure circumstance. It's undeniable. The evidence is right there, and unfortunately I should have tried to run down all the bump testing results. I could have shown them to you, you know, specifically, but that's kind of what we're talking about there. All right, I'm sorry, go ahead. All right, we're almost to the end of the stator here, and the last real stator components I wanted to talk to you about. We got the electricity inside the winding, goes out the end windings. We got the phase leads that go up to the phase rings. Now we got to get that power from the phase rings out to the isophase and out onto the GSU and out onto the grid. So there's two ways we have to get that power through the generator frame. On air-cooled units and so on, it's no big deal. It's usually done with a bus connection. A lot of times there's flex links that go in, and I know there's a lot of things going on right now with the 501Fs and some of the Aeropack and even some of the modular main leads and flex links. But you have a penetration through the frame. There's usually a clamshell or boards that go down in here and allows that power to get out of the unit and into the isophase to go out to the GSU and on the grid. One thing I'll mention about maintenance on this, in areas that have high tropical storms and stuff like that, you gotta watch these clamshells, and at the joint, it's a good idea to make kind of a labyrinth or an overlap or a step so that moisture can't protrude between those joints. We've seen quite a few failures on some of the air-cooled machines because of that. And as part of your maintenance, or definitely as part of a rewind, this is something you can upgrade to help prevent that if you happen to live in a tropical area that's sensitive to a lot of the storms where you get sideways, you know, moisture going. In the hydrogen cooled machines, you got a much more robust stator, and you've got to be able to penetrate through and keep all the hydrogen in. So you have some type of a bushing configuration, and you can see the bushings down here on this connection head. Okay, oftentimes there'll be a flexible link somewhere in here, and then you got your leads that transition through that area, and there's usually a baffle here. But this is still hydrogen environment. The real seal is out here at the bushings in this area, and it allows that energy to be transferred, electrical energy to be transferred through the bushing while maintaining the hydrogen inside. So that's the last of the stator components that we were really going to talk about. Now, I've tried to keep up with a lot of the questions, if it's all right with you guys, so we try to stay somewhat on schedule with, you know, Scott had mentioned they wanted to go out to 3 hours, and I think we're basically right on track. And if it's all right with everybody, I'm going to just continue on, and we're going to get into talking about rotors here a little bit, if that's all right with you, Scott.
That's great, Howard. Everything's going smooth.
Yes. What's that?
Yeah, that's great. Let's get into the rotors.
Okay. Just a general picture, just as a slide. This is a site that had, you know, 2-on-1 combined cycle. So we had 2 rotors during a major maintenance outage. So a lot of logistics and work that has to go on. But as we start to look at the rotor, the first element is certainly the forging. And if you're not a metallurgical person, it's important to understand that this word forging has a very significant meaning in the way the steel is processed. And actually, the steel alloy is this item you see that, you know, out here, and that's the alloy itself. But how it's processed is in a forging to give this, you know, very robust characteristics. Now, I will say this: in some very old machines, they used to have problems with the older steel where they got impurities that would cure in the center of the shaft. And back, going back 50, 60, 70 years ago, they had that issue. Today, the newer machines and most of what we would have in combined cycle applications really don't have a big problem with that. But we have more than enough other ones that we'll talk about as we go through. But anyway, this is the rotor forging. We got a radial stud right here. This is a channel for what's called a J-strap. So the electrical energy is coming up through that radial stud to the J-strap. J-strap comes around and hooks around and would connect either to the bottom or the top of the number one coil. Most common is to connect to the bottom, but there are some interesting designs that do connect to the top, okay? These are all the slots for the coils on each side. Here's a pole head, okay? So this is actually the steel that becomes a magnet because we're wrapping the copper around it. And so as we look at this, here's the number one slot here, here's the number one slot here. And just is not uncharacteristic. This is a little bit, I'm sorry. Okay. This is a little bit shorter slot than the others. There'd be number 2 slot, number 3, and they correspond. Somewhere up in the middle, this half of these slots on this side would go to this pole, as would these, and then the other side would go to the other pole on this 2-pole machine. And so that's basically the forging itself. And we should say, here's the wedges up at the top, and just like the slot, the stator, the wedges on the rotor are designed to keep that conductor inside the slot. And we'll see better pictures of that here in just a little bit. Here's some examples. This is, I think, of the same rotor we just saw. To talk more about the anatomy, this is a fir tree wedge design. This is kind of a dovetail or a T-slot wedge design you see up here. This actually has a stepped slot, meaning it's a different width up here at the top, a little bit narrower here, a little bit narrower here at the bottom. And this is probably a sub slot that you see all the way here at the bottom. In this design over to the left, this is this fir tree design. And you'll see that it's got this channel down here at the bottom on 2, 3, 4, and on out. This is designed to allow the gas to go under the coil stack so it can be exhausted up through radial vents into the air gap, okay? And there's a shelf that's put in here. It's either incorporated on the first turn or it's a material that's put in before the first turn. The first turn would sit on top of it, but it's intended to allow the coil stack to sit above and remain, have that channel remain so the gas can flow down through it. So, but that tells you a little bit about the wedging. Now, inside of the rotor body, one of the installations that we have, or one of the systems we have, is what's called the slot liners, or some people call them slot troughs, or whatever it is. But it's basically the insulation to protect the rotor coil from going to ground in the forging. Okay, if we go back here, the coil is going to sit in here. If we put just the sheer copper in here, it's going to go to ground. So you have that slot liner that is the interface between the coil and the core, so it does not go to ground. And these are some of the liners in a very raw format. We manufacture these in-house. We also buy them outside, but in this form, they're a little bit longer than they should be. They're probably a little bit taller, and you can see some of the material. This is a composite Nomex configuration, and what they'll do is they'll cut them to height and they'll cut them to length, and then they'll be utilized in the machine. Ken asked if all rotors have a center bore hole for using a bore scope, and the answer is newer units most likely not. The older units do, because the hole was used to do 2 things. One, it bored away the impurities or the inclusions that could lead to stress cracks during later operation of the unit. And so over time, what they could do is they could go down that area that was relieved and machined out, and they could hone the sides with a hone, just like you'd hone a cylinder on an internal combustion engine, if you can understand that analogy. Once they would hone it, they would get in there with the bore scope inspection, and they would look for cracks and findings inside that area. And so on older units that have that is something you need to pay attention to. And you can go in there and further what's called bottle bore to remove indications. But when you do that, you need to make sure you still got enough material left, and you do have to do an analysis to make sure you still have a mechanically reliable forging, for doing that. Anyway, so that's the slot liners, and hopefully that helps you a little bit, Ken, on the boresonic inspection. And it is using a bore scope, but they traditionally call that inspection technique a boresonic, test of the rotor. I see Jamie asked a question about, are brush generators more susceptible to failing, and LCID need stator rewind restack? I would probably say not necessarily, but that's a generic thing to one particular OEM. And there are a number of different designs, from salient poles to regular cylindrical designs. And what I would tell you, Jamie, is one of the things I tell people, it's so important to understand your machine design, and then also understand what the industry experience has been with units of your type, and then what the history has been on your unit. And that will help you a lot to understand that. Now, failing in LCID, we look at usually 100 milliamp threshold. You'd have to ask yourself exactly what's going on and why. And to fail in LCID, it's usually the criteria is usually anything above 100 milliamps. But if you have that, you have to ask, why do you have that, and what happened? Can you see signs of it? Oftentimes, it can be corrected. And past that, Jamie, I'd be happy to talk with you and talk about your individual circumstance, but I would not say that there's any one particular OEM that has a characteristic of consistently failing that, or they wouldn't be around very long. But I hope that helps answer your question a little bit. And if you call me, I'd be glad to talk to you more. All right, so going back to the rotor here and going through stuff, we got the slot liners and we got the forging. Now we're going to put this stuff together. And, this is inside the shop. You basically have the forging here. Usually there's some what they call temporary blocking that's used, and this is an assembly aid. Sometimes it can be a glass laminate or a G10, G11. It could be old micarta. It could be maple is a very common thing. I think that's what you're actually seeing here. But those are put in there so that as the coils are wound, the pressure, it helps to support the bottom of the coils so you don't crack the liners that get put in, and so that you keep the coils in the right position through the winding process. Now, the coil itself that goes around that pole that creates that electromagnet on the rotor, okay, they're just like a big rectangular slinky. And I'm probably showing my age, but I don't know that younger folks even know what slinkies are anymore, but they're round and they go back and forth. Well, this would be like an accordion too. You could spread this out and they're all connected. This is more of an older design if it's a continuous winding. But today, much more of the coils are made, and especially because of cycling, they're edge bent. And then you have a braze joint in the middle of the saddle. And going back again to the Alstom design, this is a common one on a lot of the Alstom machines. In fact, on the larger ones, on those WX and WYs, that braze joint in the middle is problematic because of some of the air channels they have in the conductor. To do that justice, I need quite a bit more time than we're going to have today. But if you're curious about that, give me a call and I can share some information with you. But the Alstom braze joint is in the middle. The original design is really only good once. You can't rewind it and have that connection remain as it is for that rewind and reuse that conductor. However, the good news is, at least for us, and I think Alstom has found a fix too, but we found a fix where we incorporate a new connector and can still reuse the copper and get away from the fragility and the mechanical problems they had in that braze region. Now, we talked about brazing a minute ago and the need for qualifications, and anybody can have a braze joint. Today, just to take advantage of modern day manufacturing and speed and cost, a lot of these edge bent coils with that joint that are either some of the radial or some of the just conventional indirect cooled machines, these connections out at the end are actually butt brazed. You have zero margin. That butt braze has to be just right. And the process is extremely important. The tooling to make it happen is important. and the qualification of the brazers, who not only understand and can execute that process, but that consistently do it, is really important with those designs. Now, I probably won't have a ton of time to talk about cyclic operation today, but one of the big problems we face in our industry is rotors that are cyclically operated. The rotor is the component that's most affected by the cycling, okay? And one of the biggest problems, there was one of the huge fleets out there that had a great what I would call a fabricated coil with a square corner design with a miter and a fillet. You know, is applied on the 786s and some others that GE had. It was a tremendous joint until you cycled it. Those things were bulletproof. And there were a lot of those machines that owners took and said, well, they were base loaded, or we just would start them up as peakers when we needed it, but they never had that many cycles added to them. But now we're going to cycle them 1, 2, 3 times a day. That joint can't deal with that square corner. It fatigues and it breaks. Making edge bent coils takes that mechanical stress that accumulates in the corner from that cycling and spreads it out to where it isn't a problem. So that's about all I can tell you about that to really get into it. Got a question about supply chain. If you don't mind, I'm going to come back to that. Good question, but give me a little bit of time. We'll come back to that one. Going back to the picture here, you can see in this slot I'm showing you right here, they've got the cell in there already, okay? And in this particular design, they're going to wind this backwards. They're going to wind the biggest coil and then the smallest at the end. Most people will start at the number 1. We do it from either end, and there are advantages in both cases, and I won't get into that now, but in any case, this is the larger coil, so one leg would go here, the other leg would go all the way on the other side of the machine, okay? Now, in this case, they're going to braze these C pieces, they call them, or half coils, in as they wind it into this machine, and they're down to the last 2 coils, it looks like. And as we look at it, here's our copper conductor going down the slot. All right, these slots are finished, and just as an FME precaution, our guys take and put tape over top of it so no little slivers of dust, dirt, or copper, even more shit, can get in there. And that's in there. Finishing up this one, they got this one. We'll replace that and put one here as well. You can see the extension of the slot liner right here, and then the coil comes out in this area. We see all this insulation that's extending out here in the corner. Those are corner pieces, and in between down here and out here on the ends, you have strip pieces of insulation that are insulating this coil turn to turn, okay? We have the ground insulation, which is the slot liner, all right? And then we have the turn-to-turn insulation. There'll be a creepage block and some insulation on the top, which is the ground plane in the slot that's underneath the wedge. And then later we're going to talk about the retaining ring, and you'll talk about retaining ring liner insulation that prevents the coils on the end winding here from going to ground to the retaining ring. All right, moving on. I showed you this picture earlier at the beginning. We were talking about intercooled rotor connections. You can see that joint I was telling you about earlier, where this machine is, instead of making this as a square, tube with a square hole in the center of it, it's made in 2 C pieces that are folded into one another. And sometimes these are brazed together, sometimes not. In cases where they're not, there's been a phenomenon called copper dusting on some of those, and it can be corrected, and it's a maintenance configuration you got to worry about. But as we're looking at the slot, here's our forging tooth right here. Okay, and there'll be another one on this side. We got our turns. There's 2 in hand, so there's no insulation between the top and bottom piece. However, between each of the pairs, there is turn insulation in between each one of these. Okay, and then we've got our ground insulation. This is the slot liner or slot trough that provides our ground plane. And then on top of that, then we got some filler materials and creepage block, and then we got our wedge. And as we said, we got holes in the wedge, so in this design, it's coming through these air channels and gets exhausted through chimneys up into the air gap, the cooling gas, okay? So that just gives you a little idea about that. I mentioned to you the diagonal flow. I love these things. This is primarily a GE thing, and they used to apply these to what they call the LSTGs. And It's really a neat design, but each one of these pairs of vent holes, one side is pointed diagonally in one direction, the other side is diagonally pointed in the other direction. It's an extremely efficient cooling mechanism, a great design, but it's expensive to make, it's expensive to maintain sometimes. And you know, that's kind of a big issue with that. We have blocking here on the end winding of the rotor, just like we did on the stator, okay? And we got the forging up here. We got a fit that we see right here, and we'll talk about the fit's actually right here where the snap ring is. And we got this extension that's going out and some blocks. All right, there's some connections coil to coil here as we look. And this is an unusual design. There's only a few of these left, but back during the war, aluminum was used as a conductor because copper was needed for the war effort. And there's still what they call condol or aluminum rotors out there in operation. Not many of them. Most of them are in coal-fired plants, so their days are kind of numbered, to be quite frank with you. But it's interesting right here. We got a retaining ring fit here that's outboard versus this retaining ring fit here that's inboard. And I'll let you contemplate that in a minute because I know I'm going to get into that a little bit more in a while. Now we have all these blocks that go in here, and they typically go in the fashion you see, and they make an angle going in different directions, and they're supported in different ways. This is a very common GE design. This one has pop rivets as the way the original OEM had, holding that tab on. We tend to modify those with one that has a double tab so it secures on both sides, but we glue it into the block and we pin it from the sides. Gets rid of the pop rivet because we've seen some of those pop rivets get loose over time, and they can wear through the retaining ring liner and create problems. So this is an upgraded blocking design. And you have blocking that's called coil to coil blocking, and you have what's called end blocking. The coil to coil blocking is usually on the sides. This is the number one coil right here. This is the pole block. It goes on the end of the pole, and it's inside of the number one coil. And then you've got coil to coil blocking as you go. Now, obviously, as you go down that conductor stack, it's tapered. So this is actually a coil to coil block you see here. This is an end block because this is a perfect rectangle. This is angular or trapezoid shape basically, okay? And they fit in there in those tabs. Some of those tabs are underneath those bands holding it, and the other tab. When this thing's operating, these tabs push up against the retaining ring and holds the wedge in place. So it means it maintains its position holding the coil. Now you might recall we talked about the axial movement of the stator coil. Well, you got to allow for axial movement in the rotor too. It's never a good idea to fight Mother Nature. The blocking, both coil to coil and end blocks, which these are end blocks that go in here, they're extending out to the end. All of these from the largest to the smallest coil back to the core. You want to try to get this whole assembly pretty much as tight as you can. Now, certain OEM designs allow for more looseness than others, but if you actually wind any of them with the right consistent philosophy, whether it's a little bit loose or a little bit tight, you're probably okay. But keeping them tight in this region is good because where the growth needs to take place is out here at the end. And these end blocks often are on pins that they can ride up and down, you know, based on the centrifugal force and so on. But you see there's pieces that are put in here behind that block. Those pieces are precision pieces to allow us the exact clearance necessary so that during operation, this machine won't expand and butt hard up against this fit out here. And if it does butt up against it, it'll cause a bow in the rotor because it's being mechanically restrained, and it'll bow it and it'll exhibit in high vibration. So it's important to understand this stuff in the relation coil to coil, you want it pretty tight. You got to leave clearance at the end so this machine can, you know, expand and contract and allow Mother Nature to do its thing. So those are important things I wanted to mention to you. Okay, the wedges hold everything together. The important thing to know about wedges is their purpose is to keep those coils in the slot. It's a pretty bad day if any one of those wedges comes loose and the coils come out. It's a big deal. The damage is going to be expensive, and the cost to repair or to replace is going to be substantial. You know, you can see on this wedge, one of the things that's important to do during a rewind or when you're doing even repairs, all of those wedges that are affected should come out, be clean. You should do end to E. If you can see carefully, there is a crack that's going across that area there, okay? And this is the dovetail fit. So all that weight is on this surface here, basically. This is just going in between the teeth here. But all that pressure that's put on that exhibited a crack, so obviously that had to be replaced. Now, the wedge materials can be different alloys, and different OEMs have different things that they'll use, but there's magnetic steel wedges, there's stainless steel non-magnetic wedges, there's aluminum, titanium, there's even brass and beryllium and copper wedges, okay? One of the things you should know about maintenance, and I know there's a question early on about flux probe testing, and flux probe testing basically is an electrical test that you can do in a high-speed balance pit, or you can instrument your generator to monitor it, and it looks for turn shorts, you know, between the turns inside the copper conductor of the rotor coils, all right? It's a great test. It's a great device, both in the high-speed balance pit and in operation. It's a very specific test. It doesn't do anything but that, okay? It only looks at turn insulation, not ground insulation or anything else, but it's extremely accurate, and it's a pretty reasonably priced monitoring system that you can do. We do it as a regular course as part of the running electrical tests of the high-speed balance operation to make sure that there aren't shorted turns, and if there are, what they are and where they are. And the great thing about that test, it tells you the coil, and essentially look, you know, in general about where it's at in the coil and which pole it's on, and it's really a great test. But anyway, the wedges, fir tree wedge, dovetail wedge, a couple other unusual designs, but you know, this is probably more common. This is an older design, but there's still a lot of these out there too, so gives you an idea of the wedge purchase. The reason I brought up the flux probe is you must have a concentric ring that follows the track of the flux probe in order for the flux probe to work. If you don't have non-magnetic wedges in that track, okay, the flux probe won't work. So if you're going to install it, you got to modify the rotor, or you got to verify that those wedges along that track are not magnetic. So that's important to know. Retaining rings. The retaining rings hold the end winding together and in place during operation. Interesting to go through the history of the retaining rings a little bit. Some of the earlier ones were what they call magnetic retaining rings, and the newer ones are non-magnetic rings. And it's really, I love to play games with people in audiences and ask them, you know, how the hell do you tell the difference? And you wouldn't believe the cockamamie answers I get, but this is magnetic, this is non-magnetic. Now it's hard to tell between the alloys of non-magnetic or the alloys of magnetic. But if you know it's magnetic or non-magnetic, go get a magnet. If it sticks to it, it's magnetic. If it doesn't stick to it, it's non-magnetic. It really is just that simple. All right. Now, as I said, the smaller machines and many of the older machines were magnetic. And one of the indications, it's not always true, but one of the indications is that probably is magnetic. You see all these holes here, which allow for radial venting due to the temperature and cooling, okay? And it's not such a big deal on the magnetic rings, but usually those holes are broached. And those broached holes it's a specific machining process which takes away stress risers on the edges of the holes. If you're changing out the magnetic ring to a non-magnetic ring to help uprate the unit, or even upgrade it, but definitely to uprate, you go to the non-magnetic rings, you still have to have those cooling holes. People have got in trouble doing that if they do not do the broaching process on the non-magnetic rings just right, because you'll get cracks that'll emanate from those holes in the non-magnetic rings if the broaching isn't done exactly right. A little less it's much more forgiving on the non-magnetic or the magnetic rings, but not on the magnetic. Now, another thing that happened in history is the newer machines were built with non-magnetic rings. The early alloy was known as 18.5 or 18% manganese, 5% chromium, okay? And the problem with that over time, as it was found, is if they were susceptible to moisture, whether because of environment or other things going on, that moisture would start corrosion of the ring, and eventually the corrosion points would make strings, and you would get stress corrosion cracking, or SCC. Okay, SCC is a common thing in many different aspects of our industry, but in this case, this is not a good thing. You don't want a retaining ring coming apart at 3,600 RPM. It's not going to be a good day to be on the generator deck. Okay, but when you're taking these apart, even the newer alloy, which is the 1818 or 18% manganese, 18% chromium, even these should be cleaned and NDE'd every single time you have the chance to do it. Now, going back to the 18.5, going back maybe, I'm going to say at least 15 or 20 years ago, almost all, if not all of the OEMs came out with bulletins that said, look, if you've got 18 manganese, 5% chromium, non-magnetic rings, they need to be replaced due to the potential problems with stress corrosion cracking. All right. And so you should know, if you have these machines, you should know what alloy you've got, know if they've been changed out or not. But no matter either way, okay, you should be doing, NDE on these rings every time they come off. Now, people ask me all the time, well, can you replace them? Yes, you absolutely can. And they're not exactly cheap. If you plan in advance, it's a lot better than if you do it on the spur of the moment, because these are a forging as well of a very special alloy. Only a couple people in the world make them. We maintain some stock. We have alliance partners that also maintain stock, and we try to share to some extent going back and forth. But it's expensive. It takes time. Can be done. Years gone by, in emergency situations, I've had customers not as bad as what you're seeing here, but they had a little bit of indications on their 18.5 rings, and they said, Howard, I got to go back together. I can't. And I said, well, it's not a good idea, but you can do some minor machining in order to relieve the indications if the indications are very minimal. But again, in almost all of those cases, the deterioration of corrosion had already started. In most cases, it came back, and the more moisture you had, the more it came back. Okay, and so it's really important. If you have these, you need to put in your maintenance plan to get rid of these and get 1818 rings. Okay. Good question from Petronella. It says, what is the risk of damaging other components when taking retaining rings apart? Can you inspect in situ? What is the risk is an interesting question, and I'll address. Can you inspect in situ? Some things you can inspect in situ. We're fortunate in our industry, the improvements in bore scopes, in their clarity and in their size, allows us to get and to do things we couldn't have done even 10 or 20 years ago, okay? So there are a lot of things you can inspect in situ. However, you can't see everything. But with the visual with the bore scope, with some electrical testing, and with some intuitive looks at history and what's going on with the machine, you can get a helpful, indication. That said, if you've got a turbine major and you're pulling the rotor out of the generator, it's a very good idea to do a rings off inspection. Now, the question of risk of damaging other rotor components. If the unit has been properly maintained and is in reasonably good condition, that risk is pretty low if you use the right procedure. And today, the right procedure, we don't use rings of fire anymore, pretty much in the modern world anyway. We use induction heating. And if you understand the design of the machine, and I'll get into the design of the retaining ring here in a moment, on the next slides, actually, you should be able to take it out with very little risk of damaging other components. Where the risk goes up is if this thing is highly corroded because it wasn't properly maintained or filtration wasn't maintained or whatever, okay? Or if they've had some failures that cause problems, yeah, there is a chance you can damage other components, but you typically don't have a lot of choice. You got to take the damn thing apart, okay? When you talk about retaining rings, and to help answer your question, the reason I wanted to deal with it right now, this is 3 different mounting configurations that are the most common in the industry. This one down at the bottom is most common for the ABB Alstom, fleets. It's called a bayonet style fit. It incorporates a shrink fit, plus you have to twist the ring slightly to align these axial ridges so that they match up, and it'll keep and prevent the ring from any kind of axial movement, in addition to the shrink fit you have on it. Not real common outside of the ABB Alstom world, okay? Up here are the more common on the Westinghouse and the GEs. I think GE had a lot more of what they call spindle-mounted rotors, okay? And these are the ones that were on the outboard, and I think I've got a picture to show you this. And this is a shrink fit. And so you would heat up the rotor and try to keep your heat fairly consistent with an emphasis on this area, and they should be monitoring the consistency of it and the temperature with a pyrometer. And there is thresholds on temperature you want to maintain and not exceed, so you don't mess with the metallurgical characteristics of the ring. But once you establish that differential between the ring temperature and the rotor forging surface temperature, you have lifting devices, and they slide it right off of the fit, and it should happen fairly easily, okay? Now, usually there is a snap ring groove, especially on the body mounted rings. These are most common today outside of the bayonet. The newer machines pretty much all have this, whether it be GE, Westinghouse, whatever, okay? And you have a shrink fit up here at the nose, and you have a little snap ring groove that you see right in here. And how you get this off is as you heat it up, you have I think it's a 1/4 cap screw that comes down, and you start, and there's ways you can determine where the split is in the ring, and you start at the opposite the split and work your way around so that snap ring gets pushed down into the hole. So when you heat it up, it'll slide right off, and then you take the snap ring off. So again, if you don't have a lot of corrosion, if you haven't had a lot of damage because of a failure, you shouldn't have a lot of corollary damage just taking off the retaining rings if you're using proven procedures and trained and qualified people. So I hope that answers your question. I see there's a follow-up. It's been said that if you inspect 18.5 rings today, you will find cracks. True? I don't know. I mean, if I could tell you for sure, I'd go to Vegas and put all my money on the line. I would say that if your environment incorporated a lot of moisture and you haven't inspected a lot of times, I would say the odds are that you're probably going to have a better chance of finding cracks than not. But the more important question is, why wouldn't you inspect it? Because you realize if the retaining ring fractures and the risk of failure, I should say the consequence of failure, you may not be repairing the machine, you will probably be replacing it. Moreover, I've had the misfortune, not being on the generator deck, but I've been on generator decks shortly after there's been major component problems like that. And you can be pulling pieces out of the ceiling and sometimes even out of the building. It's a catastrophic failure. You don't want that to happen. You need to do proper maintenance. And if you're not sure of their integrity, you better find out. And better yet, knowing what all the OEMs say and knowing the potential for stress corrosion cracking, replace them. Plan for it, order them in advance to get a good price, get them prepped and ready to go, and change them out. So that's one of the things I wanted to share with you in regard to that. All right, just going on the last slide, we were talking about body mounted. We can see the fit up here. We can see that snap ring groove right in here, and this is shrunk on to the forging. This is just an end block that's in here. Some people call this the centering ring and so on. This design over here, it's not been cleaned up and everything, but here's the rotor body up here. You got all your coils and blocking and everything. And here is the spindle mount, okay? And this is the shrink fit that retains it. Now, one of the things you also need to know about spindle mounted rotors, and GE did come out with some TILs that talked about this, on this design, and the reason it's not used a lot anymore, is during cycling and everything else, as you go up through and down through the speed range, the flexure of this retaining ring, when you're going through criticals and everything else is startup and shutdown, the flexure is happening out here because this is your shrink fit. So it's held hard to the forging right here, but this end tends to flex quite a bit more than you would anticipate actually. In this design, it's held tight to the spindle and it butts up against the forging here. And what happens over time is it allows these strands to flex with the retaining ring, and what you get is a phenomenon known as top turn cracking. And there are modifications you can put on these rotors. You can even put in dead turns on some of them with a beryllium copper on the top. There's things that you can do, but you need to realize that these spindle mounted machines are susceptible to top turn cracking, and it should be easy for you to find the stuff in the bulletins from GE and others on it. So that's kind of what we wanted to do there. Now, again, we're with the Awesome Owners Group, and this is the bayonet style ring. This is obviously an illustration. You got the bayonets over here. You can see the ribs. And what you do when you go to install this, you'll be heating up this ring with induction heating, and you'll line up the ribs here with the troughs here. And then when they pull it on, they'll twist this ring a little bit so those ribs line up with these ribs, and that holds it on axially. They don't have a snap ring that holds it on axially, all right? But there's still a shrink fit in this trough, and obviously this one hasn't been cleaned up and prepared and NDE'd and stuff ready to go back on, but hopefully you can understand what I'm saying there, and that's kind of what you're dealing with. There's a question here about smaller air-cooled machine. Now GE does not pull rotor as often, only robotic inspection. Well, I don't know if I'm going to hit on robotic inspection a little bit later or not here. We're going to be running out of time eventually, but I will tell you this. When you say smaller air-cooled, the robotic inspection is limited by three things: thickness of the robot, thickness of the air gap, and the relationship between the step iron and the nose of the retaining ring. And we have robots, with our alliance partners and so on. We do it a lot, all right? And robots are a good way to inspect and look at things. They can't take care of all the retaining ring. However, there is some evaluation you can do, and that gets into a specialized area too. But the robot is restricted when you get down to about the 100 megawatt threshold, and some of them go down a little bit smaller depending on the age of the machine and depending on the design. But right around 100 megawatts down to about 80, maybe up to 110, 120, the limitation of the current day robots, they may not be able to get in. Now, if you're talking about one a little larger, like maybe 150, 200 MVA, something like that, robots can probably get in. 7FH2s, they can get in. All right, and any of the machines above that size, 7FH2s are about 230 some MVA or something like that. And you just got to be careful that size. The need to do the NDE and the checking of the rings is to a certain extent based on, one, what you've got, two, how you've treated it, and three, where you're at since the last inspection and what condition it was in at the last inspection. Okay? If they're non-magnetic 1818, if you're taking really good care of it and you're not allowing the thing to see much moisture, even though it is 1818, I wouldn't be tremendously concerned with it. But again, all companies are trying to push the durations between majors, but I think it's probably safe to say that in a 30-year life of a machine, you'd like to see the rings pulled, probably twice in that period of time. And but you've got to do a little bit of thinking about what's your actual circumstance. So Sunil, I hope that helps you a little bit with guidance. I'd be glad to talk about it more if you want to give me a holler, but that's probably what I can tell you about that in this form. Going back to what we're talking about here, I wanted to talk a little bit about the connectors and the winding on the rotor here a little bit. This is looking at the end of the rotor. That's usually the outboard end. Some people call it the exciter end or opposite turbine end. whatever you want to call it. But this end has all your connections. And I talked to you about the radial stud that's coming up here. In most cases, it connects to the bottom coil. You can see we got series connections up here. See that little dip there? Connects to number 2. It comes down. 2 connects to 3. Goes back up. Got another connector over to 4. Go down to the bottom of 4. Connector over to 5, and so on. Okay. And you got blocks between all of this. They got a centering ring here at the end. We're going to have a nice space between the centering ring so it doesn't bottom out. There are those pins. There's that block. You can see there's a generous space in between there. Nice design. Here's the retaining ring up here. And we know from experience that we just learned this is a body mounted retaining ring. It's got a little snap ring in there to hold it axially. Got the centering ring out here at the back. Radial lead, we got a terminal stud that goes down in here, and it's drilled into what some people call the bore copper or the axial lead. All right, and this is one pole. This is the other pole, and you can see the big insulation between it. Usually there's a tube that goes around these and so on. And this is your forging and so on. This is your rotor body up here. This is the end going out towards the bearings and so on. Got a radial fan up here. In this case, they're bolt on. So that's what we got. The thing I want to talk to you about is we're going to talk about pole-to-pole connectors, talking about coil-to-coil connectors, and we're going to talk about main lead connectors here real quick so we understand. Here's another illustration that shows it to you a little better. This one has 2 radial leads here. We got a set of collector rings that are out here. This brings in the DC power from the excitation system and basically gets it in. You got a radial lead here and a radial lead here. They put the power into each of the axial leads, which goes down. It's hooking to another radial lead that goes on both poles. And then those radial leads are connected to a J strap, which will come down, hook around, connect to the bottom of the number 1 coil. Got a bearing journal here. We'll get into bearing journals. Oftentimes there's oil seals and hydrogen seals that go in depending on the design of the machine as well. So another depiction of the coils and so on. I might have showed it to you earlier. Here's the main lead connecting to the bottom of the number 1 coil. Here's the radial stud. Here's the seal. This looks like it might be a conventional hydrogen unit, so they got to keep the hydrogen inside from going down in the shaft and going out of the unit. Here's just a better up close picture of that. This is a beautiful joint. Got a nice gentle radius here. We don't have any of these conductors that are stressed tremendously. One of the problems on some of these designs, though, and some of the manufacture this braze to the stud of this shunt pack or this stack of laminations, they allow that braze to migrate or through capillary action or whatever up into this area, takes away some of that flexibility. There have been a lot of failures because of that. Here's a design where the main lead is connecting actually at the top of the coil. Not terribly common, but it's not uncommon. Most of them do connect to the bottom of the number 1 coil. We talked about a J strap. This is a J strap. This is the connection to the bottom of the number 1 coil up here. Here's the hook, nice gentle radius. It gets wedged into the surface of the shaft. And in this area, either gets brazed or bolted on to a radial stud and so on up in this area. Now, again, talking about the Alstom units, we got to have a connector that goes from one pole to the next. This coil that you see right here is the largest coil on this pole. That coil you see over here is the largest coil on that pole. Alstom did something interesting on this, and I kind of loved it when I first saw it because I thought, well, most of the pole-to-pole connectors are out here at the end of the windings because that's the area where the coil moves the most. And so the pole-to-pole connector, if it has enough flexibility built in the right way, well, they're pretty reliable. Well, Alstom says, well, shoot, it moves less up here close to the forging in the slot, okay? So we're going to put that pole-to-pole connector up here. Hard to see it in this picture, but that's a solid kind of a T-piece of copper, but it's solid. And you see that discoloration right there? Well, guess what we got right here? Okay, and I think we got another one right here, different one. But you can see they got a crack there. So this is the coil on one pole, this is the coil on the other one. Again, you're fighting with Mother Nature. When I said the coil moves less up here, I didn't say it didn't move at all, but it moves less. If I handed each of you a piece of copper that's 1/4 of an inch thick and 1 1/4 inches wide and any length you want, how many of you could stretch it about 3/16 of an inch? That's what you'd have to be able to do to avoid this cracking. So not a good design. It is something that can be changed out, modified. Fortunately, we've done a lot of them. Very common on the XWYs, anywhere from the smaller ones that are in 100 and some megawatt range, all the way up to the 300 MVA units. So that's a common configuration of them. You see it's solidly brazed here and here, has no flexibility. Pole-to-pole connectors are a problem on any design that doesn't have flexibility built into it, and there are a number of them. One design that has flexibility, but it had other problems, was on the Aeropack, the Westpac, and the Aeropack 2. And they have another problem because they transition the copper conductor through a shroud. And that transition had some sharp angles, and because of cyclic stresses and so on, you know, they often have a mechanical failure, and they have a problem too. But there are some others that have problems because they don't have flexibility, but that's an exception to the rule. The Aeropack and those other ones have the flexibility, but they didn't consider some other mechanical considerations. Now, we talked about the coil-to-coil connectors. This is just a better picture showing it to you. Now, how is this, you know, I'd like to ask you, how is this retaining ring put on? Do we see a fit up here? No, that's actually the end blocks. The fit is back here. So we know this is spindle mounted, and you've all been educated on the potential for top turn cracking if you have a spindle mounted unit, so keep that in mind. But in talking about the construction, we got a number one coil right here. Obviously, this is a coil-to-coil connector going from 1 to 2. So with that in mind, we know that that main lead is connected to the bottom of the number one coil, okay? Coil 1 to 2 on the bottom, coil 2 to 3 on the top. Here you see the connector, 3 to 4, bottom, coil 4 to 5, top, 5 to 6. And on the bottom is where we would have that pole-to-pole connector that goes from the one pole coil 6 to the other coil pole 6, and has flexibility in between it, so that as this unit's coming up to speed and wants to expand, when it's coming down, that flexibility keeps the material from, you know, forming cracks that propagate from that stress of flexing back and forth like you would a coat hanger. All right, collector rings. These can be various shapes and sizes, and their primary shape and size is due to how much current they have to carry. Some critical things you got to know is they connect usually to radial studs or some kind of configuration to get the power into the rotor. There's a radial stud hole there. This is one here, and that's one over there, I believe, on this unit. This one only has 2 rings, a smaller unit, not as much current. This one has 4, but obviously these 2 are tandem and these 2 are tandem. Same up here. These carry more current. In smaller units, you can find these where they're solid, but traditionally, most of these have a spiral groove inside of these. That spiral grooves help to maintain proper commutation and any kind of dust you get from your brushes and so on. Some people also call them dust grooves. They would go into those and they allow them to blow out through that and to not interfere with the commutation. It's important to have the right brush grade because the carbon itself puts a little bit of a glaze on these surfaces so that it properly slides mechanically and allows for proper commutation electrically, okay? These have insulation that protect them from the shaft over time. That can go bad and they can be rebuilt. They can also be replaced. And, you know, people always ask me, well, God, what's the matter with that one? It has all those holes on either side. And again, if we were all together, I'd ask you, what the hell are those holes all about? Well, you got a lot more current because these tandem rings, and these are pretty large ones up here. Those holes are actually maximizing surface area to help keep the ring surface itself, the temperature cooled, okay? The hotter you make it, the more you can interfere with the brushes themselves and the commutation. So those holes are nothing more than a cooling vent, and they give you some cooling into the ring itself. So. All right, one of some of the last components of the fans. There's basically, you know, 2 primary types of fans, the squirrel cage and the axial fan. Today, a lot of the axial fans are bolt-on. They look more like a turbine blade, either with a root or with a some kind of rabbeted channel, allowing them to bolt on with a great deal of security. On the fans, the thing you got to know from a maintenance standpoint is a lot of these squirrel cage fans are fabricated, and it's not uncommon to find cracks in the areas where they're welded and in some of the components that they're made with. So major outage, clean them up, and as a minimum a visual inspection. But if you're rewinding, very good to clean them completely, do a complete battery NDE before you put them back on. Same with the axial fans. There is some ability to re-weld and to repair some of these depending on what you find. You cannot repair them in all cases. And when you do try to repair them, it needs to be done by somebody that understands the alloys, both of the base metal and of the welding that you're doing, and also understands stress relieving, because it's very critical. You can also replace some of these. Somebody asked something about EM designs, I think, a little while ago, but the EM designs of some of the older units, they have a hoop that goes across the top of the teeth on a very similar design, but it was fabricated. These blades were welded on, and sometimes those hoops come loose and it'll damage the stator end winding, and there's a modification. You can replace the fan completely, where it actually has one less blade, but it goes up taller. You get rid of the ring, and it's made out of one solid billet. But fan maintenance is important. Obviously, the purpose of the fan is to force cooling and to direct that. And, you know, there are different configurations. Some of them push, some of them pull. Getting them on in the right orientation is very important during maintenance. Most houses have pretty good procedures to keep that in check. And you need to do reasonable maintenance on these things over time, especially during major rewind and so on. And the last items of the bearing journals, obviously, the bearing journals and the bearings themselves. Obviously, you know, we were talking about the end bell or the bearing support brackets and so on. This bracket has the bearing integrated inside of it. These are the shafts, and there's a lot of maintenance that goes into oil and oil contamination detection and understanding what's going on there, but also maintaining the surface and the clearance, as well as not too much of a clearance. So, you know, there's maintenance that needs to go on here. And as you're changing out bearings or doing rewind, you should be checking the journals and the oil seals, hydrogen seals, making sure everything's in check. A lot of bearing failures. The biggest probable cause is because of oil contamination. And most good maintenance programs have a very good program for monitoring the oil and filtering it and taking care of it or replacing it. But this is the consequence, and it can lead to a really ugly event for the overall machine. But the purpose of the bearing is basically to support the rotating element inside of the frame and the end bells and so on. And there are a lot of different types of bearings, from standard sleeve bearings, tilt pad bearings, even large rollers and other configuration, tapered rollers, and some smaller and other offshore machines and so on. So last thing I want to tell you about the rotor is high-speed balance, and this really isn't about a component. I put it in because there's a misnomer about high-speed balance. Everybody thinks, because of the name, that the purpose of this is the high-speed balance. And I'm here to tell you that I don't see it that way, okay? The real purpose of high-speed balance is to requalify this rotor mechanically and to requalify this rotor electrically. Oh, and by the way, because we have it in this fancy facility, we'll balance it too, okay? But the important thing is to requalify it mechanically, requalify it electrically. And the way to do it, once you get it set up and everything's in order down here, and these trunnions obviously would be taken out of the way, they're just putting on the bearing caps down here at the end. But once they get everything assembled, they roll this thing out, get it normalized, make sure that all the force lube system and all the lift systems are all operational and been checked. They're going to try, the first thing they're going to try to do is they're going to run this thing up to overspeed. Hold it for a minute and come back down. Overspeed from a maintenance standpoint is 10% over, or 110%, okay? When machines are typically manufactured brand new, they traditionally go to 20% over, okay? Now, there are people saying, well, Jesus, if that's good for brand new, we ought to require it for rebuilt. It doesn't work that way, because you're not considering the stresses that are put on the forgings and on many of the components. And most repair houses and many of the OEMs on rewound machines, their insurance policies and their internal policies say, look, we're only going to 110%. We're not going to 120. So just keep that in mind. But going back to the process, once you get up to 10% over on 3,600 RPM, that'd be 3960. You hold it for a minute, you come back down. Before you put that rotor in the pit, you did a complete set of total indicated runouts, or TIRs. And you're going to do another set of TIRs as soon as you hit overspeed and hold it for a minute. So you're going to be able to tell if the rings have moved adversely or if they're seated in an unusual position. And the TIRs that you're producing the second time as compared to the first time are going to help indicate that to you. In addition, you're going to use a bore scope and a flashlight, and you're going to visually inspect to make sure that nothing else has moved adversely as a result of going up there to overspeed. And if everything looks good, if all your TIRs match their reasonable expectation, you just requalified the rotor mechanically. People all the time ask me, well, Howard, what's the difference if I requalify it mechanically or I don't? And I said, well, here's an analogy for you. If I take you to your development and I stand you between your house and your neighbor's house and I have a hand grenade and I pull the pin and I hand it to you and I say, okay, pick a house. I don't know about you guys, but my neighbor would enjoy his new house because I want to keep mine. If you put a machine into your generator without having a good idea of its mechanical integrity, I don't know that it's that much different than the hand grenade scenario, okay? That's why you requalify it mechanically, and it's something you should incorporate. Second, we talked about the electrical aspect. Here's a flux probe in the balance bit. Obviously, inside the stator, they're quite a bit smaller, okay? But the flux probe comes down. It's riding along a concentric band of non-magnetic wedges, and you input the data on the number of turns, number of coils, so on and so forth, get the system set up, and you run it up through and down through the speed range, and you can see if any shorts are coming in or going out, or if there are any shorts that even stay, all right? If you got to find something that stays because it's easier to find later. The ones that are a nightmare for guys like me that are trying to help customers with the problems are the ones that it comes in at 28 or 3,200, and when you come back down, you go below 28 or 3,200, it goes away, and it's hard to find sometimes. The flux probe does help you because it tells you which coil, which turn, which pole, and it really helps a lot. But great diagnostic device, but it only does one thing. I have people tell me all the time, well, I want to run a flux probe to see if my rotor's grounded. It doesn't do anything but look at turn insulation and look for turn shorts inside your rotor winding. That's all it does. So that's basically the rotor aspect, but I wanted to touch on brushless exciters because a lot of the modern day machines have brushless exciters that are either shrunk fit or they're directly bolted on to the shafts. And, quite often you'll see, something like this, either a disc or another configuration that is in there. Brushless exciters in of themselves are very unusual machines, and it's hard for people to understand, but this is a Westinghouse, I think it's a Mark III brushless exciter, and it's a pretty large machine. It's got a double diode wheel over here. We got the AC exciter and the field frame in here, and we got the bearing here, and then we got the permanent magnet out here. So people get confused about how this dang thing works, including me at times, but this is basically it. The one thing from a safety standpoint I want to warn you about, especially on this design, those permanent magnets are extremely powerful. If your people go in there and play around and think they can remove one, the worst thing that can happen is it can injure the person. You can lose fingers and other stuff because they're so powerful. If you get them loose and they break loose, the force is just tremendous, okay? But the other thing that happens, and what a lot of people don't know, if you remove one of the magnets from the assembly, you actually compromise the magnetic field in this device. You got to get it reassembled, You got to jog it down or short it out so that it's not done, and then you have to remagnetize it above the Gauss level you were looking for, and then you jog it down to hit the target Gauss level. So the permanent magnet generator that you see has a little armature, has these permanent magnets. That's the energy that starts everything off. Goes down through the armature, okay, comes through the bearing, comes down, and then you've got that DC energy that's put into the armature, excuse me. Yeah, put the DC energy into the fuel pole and then into the armature. It runs it out to the diode wheel assembly because you got the AC armature and the exciter. This converts it again to DC, puts it either out to the slip rings or onto the shaft. That's your DC that's going onto your rotor, okay, to run the generator, okay? So brushless exciters, they all primarily operate in this way, but they may look like this. They may look like a disc, but they're essentially operating with the same components, just a little different configuration. Maintenance-wise, one big thing about these things is they don't like to be dirty, all right? So cleaning is a big deal. You got to keep track of the fuses and diodes. Almost all the OEMs recommend that you take and that you have a spare set of those in stock. You got to be careful of the range of their characteristics electrically, and the instruction books will tell you more about that. There are a number of other things, but those are some of the general things that you want to be aware of on the brushless exciter. So I mentioned to you other generator resources. Check this out. If you're not a member of the International Generator Technical Community, I suggest you check it out and you take a look at this forum. It's just a tremendous resource for information. You can ask questions. You can go to the library. And one thing I will say, as I said, I think I saw a picture of Clyde Munn's photograph early. His whole dossier that he compiled over his career, which is tremendously impressive. All right, it can be found up there in the library at the technical forum. So I encourage you to go take a look. And here's another picture of that. Now, since we got a little bit of time, I'm going to rush through this really quick and talk about some of the generator maintenance that we may not have hit on. There's a lot of cycling stuff you need to be aware of. It's really a big problem. We're under tremendous pressure commercially to extend outages, to spend less money. There's just a lot of stuff going on that really is making the maintenance activities challenging. This is what we're trying to accomplish when we're trying to inspect and test as part of the maintenance outage. We want to monitor, identify, evaluate, qualify, and quantify, and then we need to trend it. This last word, I wish I was with you guys all face to face because I'd ask you, and if you were all telling the truth and I had you on a polygraph test, I'll bet you over half of you do not effectively trend all of your data. And this is really an important part of maintenance, and you should do it more than what a lot of the folks do, okay? Another thing you can do to help yourself as part of the maintenance is become aware of the characteristics of your generator model and also your specific machines. Here's some sources you can use to try to go do that, all right? And it's important because this can be invaluable information, and you don't have to pay much money to do it. Even if you have to pay a conference fee or a video conference fee, it's invaluable in what you're going to gain. Visual inspection has been called the best overall maintenance value you can get, but it really needs to be done by trained and experienced personnel. That's where you get your biggest bang for the buck. But this is still true today, even with technology. The visual inspection is incredible. I talked to you about the borescope improvements in both clarity and color contrast. You can even measure inside some of the best borescopes to close to 1/1000th of an inch in looking in areas. So it's a great technology tool. I want to share a little bit about robotic inspection. I mentioned it earlier. This is becoming more common, and there are limitations, and I mentioned some of those, and I'll hit it again in a minute. But this is the actual robot of the trolley that goes inside. This is the umbilical cord that goes out. And this fits into the air gap, and it has tractors on this model that goes up against the rotor, that goes down against the stator, and you can actually drive this sucker. And I'm really showing my age because it cracks me up because the controller on this thing is actually, believe it or not, you can't see it in here, it's a handheld controller, but it is actually has the words Xbox on the controller. And the folks running it, I can understand why. They're of the age that they hone their skills playing the game, but man, they can manipulate this thing like it's nobody's business. They do an incredible job. This is the control station for the robot, and it's really impressive what it can do. Now, as I mentioned to you, the thickness of this relative to the air gap and getting past the step iron and the nose of the retaining ring to get into the air gap, that's the limitation, okay? And this talks about, you know, the size of this crawler, and it's basically 9/10 of an inch in thickness, all right? So you got to watch what the air gap is. You got to be able to get it in there. Now, what it can do for you is that it has tremendous visual capability. It has forward-facing cameras and forward-facing video. You can see a lot of stuff. This is just a representative sample. I'm not terribly concerned by this picture, but you got a little bit of flaring laminations, but this is an example of the upward-facing camera looking at the stator core, all right? And this flaring is not something I'd be tremendously worried about, but if I saw major dings from foreign material, or I saw major rust that I thought might be causing interlaminar damage, you know, the robot can help pick that out for you. There's also some downward facing cameras, and this is looking downward onto the rotor. You can see the vent holes that are right here on the radial cooling of the vent hole. Well, this is that radial hole, and it's looking down there, and this is the filler on the rotor. And this is what some people call a slipstick condition, where the amortisor and the creep that's blocking the filler was able to move, and so it's partially blocking this cooling hole. All right, the robot picked that out. The plant wasn't aware of it, because fortunately this isn't as bad, and it wasn't terribly, you know, fraught throughout the whole machine. But obviously this whole slot, okay, had that, because all the vent holes will react the same as you go down, okay? But it can find that as well. And there are fixes on this. This is a common problem on some of the 7FH2s that haven't had the modification to the rotors. Two other things that it can do, and these are options. Normally, if you go to get a robotic inspection, you get a question about the LSIT on the 7A6 units. I'm sorry to tell you, no. The 7A6, it cannot. The 7A7, it can. There's just small difference there. The 7A6 we're expecting with the new generation that we're already looking into and maybe getting, it isn't out on the market yet, but we think it will be able to do the 7A6s and some of the smaller units. So, Sunil, I hope that answers your question there. The other thing, it does do the digital wedge tap. This is usually an extra cost over and above, you know, the visual and the video documentation you get. It's not a big deal, but it goes through just like you would if the rotor was out and you're using a handheld trolley or whatever, and you do a wedge mapping and you look and evaluate the wedge mapping based on that, okay? And here again is the other thing it can do. It can do an LSIT of the core itself, and just like the handheld, you're looking for any deviations that are above 100 milliamp. This was a really bad one, to be quite frank with you. It's hard to see the scale, but the line where my cursor is at, that's 400 milliamps, and you can see there are a number of peaks that are getting really close. Some of them were well over 300 milliamps, so this core had some serious problems, okay, and had to get some other work done to it. But this is what the robotic inspection can do to you. Still pictures, excellent video, tremendous clarity, can look at the rotor itself, the stator itself, and can look axially anywhere in the air gap as you're going along, so you can see wedges and other things. It can do the digital wedge tap, it can do the LSID. Great maintenance tool. It can save you from taking the rotor out in some cases. Now, listen carefully to what I'm saying, because people seem to gloss over this. If you have a machine that has known problems, okay, why would you want to do a robotic inspection? The answer is pretty simple. If we do the robotic inspection and we find the problems, what are we going to do? We're going to take out the rotor, okay? And the cost of this robotic, it's not tremendously expensive. They can range anywhere from about you know, maybe 45, 50,000 for all of this to as much as maybe 100,000, depending on the unit, the size, the number you're doing and when you're doing it and all the different things. But that gives you at least some kind of framework as a range, all right? Not terribly expensive. Why would you waste that when you know that you got problems? Pull the dang rotor and deal with the problem, okay? But if you think your machine is in good condition and you just don't want to do, you want to do a cursory check without pulling the rotor while you're doing other turbine work or other things, this is a fantastic tool to help you get insight. But don't be surprised if you find some things. Some things you may find you want to note them for your next outage when you will pull the rotor. Or some of the things you might say is, holy cow, I can't let that go. I need to get into it now, and you're going to pull the rotor. But start with good thinking when you're planning your outages, please. All right, access that you need. To get the robot in, you need to, as a minimum, just to do all the visuals, okay, and to do the digital wedge tap, okay, you need to have at least one end, the upper end bell off, so you can get the trolley or the robot in between the retaining ring and into the air gap, okay? Now, if you want to do an LCID, you have to take off, oh, sorry, going the wrong direction here. You have to take off the upper end belt on both ends, because just like with the regular LCID, you've got to put a trigger coil or the excitation coil around the unit and through the air gap. So you have to have the other end opened up, okay? And that's just a little bit of, if you're not aware of that, if you want to do the LCID, you got to have both ends. You want to do the other three things, then you can just do the exciter end usually, okay? And I was just going through these. I just think I explained all that to you. So anyway, I'm going to breeze through these slides. What I tried to provide you with here is just some guidance. These are standard monitoring from the control room you ought to be doing. It tells you how often you ought to be doing it. It tells you what you might find and what the activity is. I got a whole bunch of these, and like I said, I'm not going to spend a lot of time with them, but here's the visual inspection, stator winding, the core, the rotor, things you ought to be looking for. This is how often you ought to do it, okay? This is, why are you doing it? This is, again, electrical tests, inspection and testing on the stator. Again, the activity, purpose findings, how often you ought to do it. These are good tools to help you with your maintenance, okay? And I'd encourage you to use these as a planning tool, as a checklist to remind you of things you might want to do. It'll also help you in understanding what things might do to help you in a diagnostic standpoint, but a lot of this is really for maintenance. And then this table was put together by a buddy of mine that works for EPRI now, but Bill Moore, I think, put this together, and it's a really nice table because it doesn't show you everything that we can do today, but it shows you the most common things that you're going to do as a maintenance activity, tells you what it shows you, and it tells you the frequency. And I would encourage you, you know, to use this, like I said, as a checklist to remind you. So final remarks, you know, documentation is a very important thing. Everybody documents stuff, and we do that. But documentation kind of tells you insight about what has happened and where you're at right now. I'm making a case again for trending. If you trend things, you trend this data you collect, it's like a crystal ball. It tells you where you're going. Another analogy is how many of you would get in your car, put it in reverse for race, and you get out on the freeway and you go down the freeway at 70 miles an hour in reverse, looking out of your rearview mirror. I hope none of you would say that's a good idea. All right. But that's not any different than what you're doing if you don't trend. You need to trend the information. Trending it, you can go 100 miles an hour if the cops don't catch you, down the freeway, looking out the windshield with good clarity, knowing exactly where you're going. Trend your data, please. Okay. Last thing that really sticks in my craw when I talk to people about maintenance is I said, well, you know, we've been looking through the instruction book. We're looking at some of this stuff here. Where's your outage reports for the last couple of outages? We had them around here somewhere. I mean, they were up on the shelf, but then I had them over in that file cabinet. Do yourself a favor. Go get another 4-inch binder and take every darn outage report, put it in there chronologically and tab them, because that is important information when you have problems when you look back on the history of your unit, you pay a lot of money for those outage reports. It is a sin not to have them in a more usable configuration and location so you can benefit from that data. And I love the 4-inch binder, put it right next to your instruction book, and it's right there for you to use. The other thing, just about every outage report I have ever seen has an area that talks about recommendations. Well, it has findings and recommendations, but the recommendations are the important thing. And I recommend to people in that 4-inch binding, put a sheet at the front and make a list of all the recommendations that have ever been made from the outage. And then look at what you've done. Check them off if they're done. If they're not done, is it still a problem? Do you need to do it? You can't ask for a better maintenance planning tool if you use it. Okay? So I encourage you to think about that as well. And with that, I really enjoyed talking with you today. I've wore you out for about 2 hours and 50 minutes, as best I can tell. But I'll gladly answer some more questions for a while, as long as you want to ask them and want to stay on. And Scott, I can't thank you and the AOG organization for giving me the opportunity to visit. And I hope it was helpful.
Howard, I can't thank you enough. That was really fantastic. I think you did a great service for the industry today, and actually got a call from Clyde Mon during your presentation, and he sang your praises, to no end. And he also believes that, that this is the kind of information that needs to be continually pushed out to the industry so that we don't repeat the mistakes of the past.
If you don't mind, I got to tell a quick story about Clyde Mon.
Go for it.
Clyde is just a fantastic gentleman, and he and I think you might have been there. We were at a conference in California. He and I were having lunch, and his wife was there, recently passed away, another wonderful lady, and prayers go out to her. But anyway, Clyde and I are sitting there, we're eating lunch, and all of a sudden, for no reason, Clyde looks at me, and there's about 10 of us at this table, and he says, Howard, I've noticed you're getting a lot smarter lately, and I about choked on my food. I said, holy cow, that's high praise from Clyde Mon. And I made the mistake of not thinking before I opened my mouth. And I said, well, what really led you to that conclusion? And he looked up and he smiled and he said, well, it's really quite simple. You're agreeing with me a lot more. So he's a brilliant man, but he's also a jokester and just a wonderful human being. So I'm glad he could stay for part of it. But that's my story about Clyde Mon.
Thanks for sharing that. All right. Well, if anybody has any more questions, you could either unmute yourself or put them in the chat, and Howard will be around for a couple more minutes. For all those users out here who have Alstom units, it would be great for you to sign up for the AOG users forum, where you can share information with fellow Alstom users. And yes, the presentation in some form is going to be made available to all the attendees, and also this recording, which will be great to share with people in your organization as a real learning tool.
Yeah, Scott, I would also say to those that are out there, I mean, I've been doing this Generator 101 with NEC and doing some stuff like this for quite a while. And we've worked with some of the insurance companies, but if any of you get a group of people together and you want to do this, if you give me some advance notice, we'd be happy to come and do it, for your organization. You pull a group together, and we traditionally don't charge for doing it. We're really big on trying to get us all as smart as we can get so we can best work together. So feel free to contact me with questions. Feel free if you want to try to do something like this, but I thank you for all your comments. You're feeding a dumb old fat bald Irish guy's ego, but I can't tell you how much I appreciate the opportunity from the Alstom Owners Group, and also always Scott helps me out and keeps me on the straight and narrow. So
thanks, Howard. So yeah, we'll be sending out the slides and the recording to all attendees here in a couple days, and feel free to reach out to Howard with any additional questions. I know there were some very specific questions that he's gonna respond to from the registration. But once again, I just want to thank everyone for coming today and thank Howard once more and the international generator technical community, National Electric Coil, and of course, your friends at Combined Cycle Journal. All right, Howard, thanks so much, and we'll see you soon. See you next week.
Looking forward to it. I'm looking forward to some grilled oysters and warmer weather than Pittsburgh.